The universe has a twisted sense of timing, and what just unfolded in the final days of September 2025 proves that reality can be stranger than any science fiction screenplay ever conceived. Picture this scenario. Two massive stars suddenly explode into naked-eye visibility. Twin earthquakes devastate Venezuela within hours of each other. And our third, confirmed interstellar visitor gets caught in the crossfire of a solar storm tantrum. All of this happening within a 72-hour window that would make Hollywood screenwriters weep with envy. If you think that sounds like an impossible coincidence, you're absolutely right to be suspicious. Because what we're witnessing isn't just a series of random cosmic events. It's a synchronized symphony of destruction and discovery that's forcing scientists around the world to question everything they thought they knew about how our universe operates. I'm about to take you on a journey through the most mind-bending astronomical convergence in modern history. We'll dissect stellar explosions that are lighting up the southern sky, examine earthquake patterns that are defying conventional wisdom, and track an interstellar wanderer that's about to experience something no human has ever witnessed before. But here's the kicker. By the time we're done, you'll understand why this week might represent a fundamental shift in how we view our cosmic neighborhood. The events I'm about to reveal span scales from the subatomic to the galactic, from split-second nuclear explosions to geological processes that have been building for decades. And somehow, impossibly, they're all happening right now. So buckle up, because we're diving into the deep end of cosmic chaos. And what we discover might change how you look at the night sky forever. Let me start with the timeline that has astronomers scratching their heads and reaching for explanations that stretch the boundaries of coincidence. September 23rd, 2025. While most of the world sleeps, a star in the constellation Centaurus suddenly erupts with the fury of 1 billion suns. This isn't just any stellar tantrum. This is V1935 Centauri, reaching naked-eye brightness at magnitude 5.8, making it visible to anyone willing to step outside and crane their neck toward the southern horizon. Within 24 hours, as if the universe decided one exploding star wasn't dramatic enough, a second stellar bomb detonated. V7994. Sagittari blazed forth in the Archer constellation, hitting magnitude 6.2 and joining its cosmic sibling in a celestial light show that has professional astronomers scrambling for telescope time and amateur stargazers dusting off their binoculars. But wait, it gets weirder. While these stellar explosions were painting the southern sky with ancient nuclear fire, planet Earth decided to join the party in its own uniquely violent way. September 24th, 2221 UTC. The ground beneath Venezuela's Zulia state suddenly ruptured with the force of several nuclear weapons, unleashing a magnitude 6.2 earthquake that sent shockwaves rippling across two nations. Buildings swayed, people evacuated, and seismographs around the world recorded the violent release of tectonic energy that had been building for decades. If you think that's where the story ends, think again. Because just 5.5 hours later, at 3:51 UTC on September 25th, the same region experienced déjà vu in the worst possible way. Another massive rupture, this time magnitude 6.3, tore through virtually identical coordinates, as if the Earth itself was having a cosmic temper tantrum in perfect synchronization with the exploding stars overhead. Twin stars exploding within days, twin earthquakes rupturing within hours. And threading through this chaos like some cosmic messenger, 3I Atlas, our third confirmed interstellar visitor, was racing through the inner solar system during what might be the most active period of solar cycle 25. Now, before you start thinking I've gone full conspiracy theorist on you, let me be crystal clear about something. I'm not claiming these events are causally connected. What I am saying is that the statistical probability of this convergence happening by pure chance is so astronomically small that it makes winning the lottery while being struck by lightning seem like a sure bet. The professional scientific community, bless their methodical hearts, maintains strict positions on these correlations. The United States Geological Survey will tell you that there's no demonstrated connection between space weather and earthquake activity. Solar physicists explain coronal mass ejections as routine features of an active sun. Stellar astronomers see novae as predictable consequences of binary star evolution. But here's what makes this week genuinely unique in the annals of human observation. We're witnessing something that has never happened before in recorded history. For the first time ever, an interstellar visitor is experiencing intense solar weather near solar maximum conditions. 3I Atlas isn't just any cosmic wanderer, it's a messenger from another star system, carrying materials that formed billions of years ago around a completely different sun, now getting sideswiped by our star's most violent tantrums. Let me paint you a picture of what's happening up there right now. Our sun, operating at peak fury during solar cycle 25, has been hurling billion-ton clouds of magnetized plasma across the solar system at speeds exceeding 1,000,000 miles per hour. These coronal mass ejections represent some of the most powerful events our solar system can produce. And according to space weather models, they're crossing paths with 3I Atlas during its approach to the inner planets. Think about that for a moment. An object that has been wandering the galaxy for millions of years, surviving radiation that would sterilize any earthly organism, enduring temperatures just degrees above absolute zero, is now getting hammered by solar storms that can strip the tails off comets and disrupt satellite communications across entire continents. The implications are staggering. We've seen what coronal mass ejections can do to solar system comets. In 2007, the European Space Agency's STEREO satellites filmed a CME literally tearing the ion tail off comet Encke, a disconnection event that demonstrated the violent reality of space weather interactions. But those were comets that formed in our own stellar neighborhood, composed of familiar materials that condensed from the same primordial disk that gave birth to our planets. 3I Atlas is different. This visitor carries ice and dust that formed around an entirely different star, in an alien stellar environment with different temperatures, different chemical abundances, different physics governing its formation. When our sun's coronal mass ejections collide with this interstellar material, we're witnessing the first documented case of our star directly interacting with matter from another stellar system. The scientific opportunities are unprecedented. Every measurement, every spectroscopic observation, every image captured during this encounter provides data about conditions in alien stellar systems that we could never obtain any other way. It's like having pieces of distant worlds delivered to our cosmic doorstep, complete with isotope ratios and chemical signatures that reveal the secrets of their birthplace. But the timing, that's what has everyone talking. The geometry is almost too perfect, too convenient for observation. 3I Atlas is threading the needle between planetary orbits with surgical precision, arriving during solar maximum when space weather activity peaks, approaching during the autumn equinox when Earth's magnetic field orientation amplifies geomagnetic coupling with solar disturbances. Professional observatories around the world have marshaled their most powerful instruments for this encounter. The Hubble Space Telescope, the James Webb Space Telescope, the Swift Observatory, ground-based facilities in Chile and Hawaii, all coordinating their observations to capture every photon of data from this cosmic convergence. Meanwhile, amateur astronomers worldwide are contributing crucial observations that professional telescopes, focused on multiple targets, simply cannot provide continuously. Their nightly monitoring creates the temporal resolution needed to detect subtle changes in brightness, tail morphology, and spectroscopic evolution as 3I Atlas responds to varying solar conditions. The numbers alone tell a story that challenges comfortable assumptions about cosmic coincidences. 2 stellar explosions reaching naked eye brightness within days, occurs perhaps once every few years. Magnitude 6 earthquakes happening within hours in the same region follows known patterns of stress transfer, but the timing feels orchestrated. Solar maximum conditions creating optimal space weather during the same week adds another layer of synchronicity that stretches statistical credibility. What we're documenting here isn't just a series of unrelated astronomical events. It's a convergence that spans scales from stellar explosions thousands of light years away to seismic ruptures kilometers beneath our feet, all playing out while an interstellar messenger experiences our sun's fury for the first time in cosmic history. The viewing opportunities for what's coming next are equally unprecedented. October 3rd marks 3. I-Atlas's closest approach to Mars, passing within 28 million kilometers of the red planet. For the first time in human history, we'll have spacecraft positioned to observe an interstellar visitor from an alien perspective. Mars orbiters, including ESA's ExoMars and NASA's Mars Reconnaissance Orbiter, are preparing for humanity's closest look yet at a cosmic wanderer from another stellar system. But the story doesn't end there. October 29th brings perihelion, 3 I-Atlas's closest approach to our Sun, when solar heating will reach maximum intensity and potentially liberate volatile compounds that have remained frozen for millions of years. December 19th offers the visitor's closest approach to Earth, providing months of observation opportunities for both professional observatories and backyard astronomers. As I prepare to dive deeper into each component of this cosmic convergence, remember that we're living through a moment that previous generations could never have experienced. We possess the technology to detect interstellar visitors, monitor global seismic activity in real time, observe stellar explosions across the electromagnetic spectrum, and track space weather throughout the solar system. The question isn't whether these events are connected by some hidden cosmic mechanism. The question is what this unprecedented convergence reveals about our universe's capacity to surprise, inspire, and humble us through demonstrations of its ongoing creativity. Because what happens next, as 3i Atlas continues its journey through our solar system's most violent weather, might answer fundamental questions about our place in the cosmic neighborhood that surrounds us. The mechanics of stellar violence operate on scales that mock human comprehension, yet what unfolded in those September nights reveals physics so extreme they border on the supernatural. When V1935 Centauri erupted into naked eye visibility, we weren't just witnessing a pretty light show for backyard astronomers. We were observing the explosive death and rebirth of a white dwarf star, a cosmic furnace so dense that a teaspoon of its material would weigh as much as Mount Everest. Picture this stellar monster, roughly the size of Earth, but containing the mass of our entire Sun. Surface gravity crushes matter to densities approaching 1 million times that of water. Surface temperatures hover around 50,000 degrees Fahrenheit, hot enough to vaporize any known material instantly. This stellar corpse represents what remains after a sun-like star exhausts its nuclear fuel, sheds its outer layers, and collapses into a sphere of degenerate matter, where atoms exist in states impossible under terrestrial conditions. But here's where the story gets twisted. This white dwarf isn't alone. It's locked in orbital dance with a normal star, perhaps a red giant whose outer atmosphere has swollen to massive proportions as it ages. Gravity from the white dwarf gradually strips hydrogen from its companion's extended atmosphere, pulling gas across the space between stars in streams that spiral inward, like cosmic water circling a drain. For decades, centuries, maybe millennia, stolen hydrogen accumulates on the white dwarf's surface, growing denser and hotter under crushing gravitational compression. Unlike the controlled nuclear fusion occurring in stellar cores, this process builds toward explosive release. When temperature reaches roughly 100 million degrees Kelvin, thermonuclear runaway begins. The explosion that created V1935 Centauri occurred in seconds. Runaway fusion consumed the accumulated hydrogen layer in a conflagration that released energy equivalent to our sun's total output over thousands of years. But here's the crucial difference from a supernova. The white dwarf itself survives. The explosion blows away only the surface layer of stolen material, leaving the underlying stellar remnant intact and ready to begin the process again. This is why NASA's Fermi Gamma Ray Space Telescope and the Swift Observatory went absolutely ballistic when they detected V193 5 Centauri's high-energy signatures. We're not just talking about visible light here. This stellar explosion was pumping out gamma rays and hard X-rays, evidence of particles accelerated to near light speeds in the explosion's shock fronts. Electrons spiraling through magnetic fields at enormous energies, creating synchrotron radiation across the electromagnetic spectrum. Within days, V7994 Sagittari joined this cosmic fireworks display, reaching magnitude 6.2 and demonstrating that the universe apparently has a sense of dramatic timing that would make Shakespeare jealous. Two stellar explosions, both bright enough for small telescopes, both occurring within the same remarkable week. The last time observers enjoyed two bright novae simultaneously was during summer 2023, and before that, you'd have to reach back several years to find comparable displays. But while professional astronomers were scrambling for telescope time to study these stellar explosions, planet Earth decided to remind everyone that cosmic violence isn't limited to distant stars. The magnitude 6.2 earthquake that struck Venezuela on September 24th released energy equivalent to several nuclear weapons, originating from just 7.8 kilometers beneath the surface. Close enough to the surface to amplify ground acceleration across a broad region, sending shock waves rippling through both Venezuela and Colombia. The seismic waves propagated outward from the rupture zone at roughly 6 kilometers per second through the surrounding rock. Primary waves, those compressional disturbances that cause back and forth motion, arrived first at seismograph stations across the region. Secondary waves followed, creating the side-to-side motion that typically causes the most structural damage. Surface waves, traveling more slowly but carrying the most destructive energy, produced the rolling motions that eyewitnesses described as lasting for minutes in some locations. Then came the geological déjà vu that has seismologists scratching their heads. Just 5.5 hours later, a magnitude 6.3 earthquake struck virtually the same coordinates, this time from 14 kilometers depth. The physics of stress transfer explains why earthquakes often cluster temporally and spatially. When one fault segment suddenly slips, it changes the stress field on nearby fault segments, sometimes triggering additional ruptures in rapid succession. But the timing feels orchestrated beyond normal geological processes. The magnitude difference between 6.2 and 6.3 might seem trivial to casual observers, but the logarithmic nature of the magnitude scale means the second event released approximately twice as much energy as the first. Combined, these twin ruptures produced energy equivalent to a single magnitude 6.4 to 6.5 earthquake, ranking among the largest global seismic events of late September 2025. Regional tectonics provide the geological context for why this area generates such powerful earthquakes. The Maracaibo Basin sits within a complex zone where the Caribbean plate grinds against the South American plate, creating a network of fault systems that have been accumulating stress for decades. These geological boundaries store energy that must eventually be released through sudden slip events, but the precise timing remains fundamentally unpredictable. International seismological agencies reported slightly different magnitudes for these events, reflecting the complexities of earthquake measurement. The United States Geological Survey uses moment magnitude calculated from the total energy released during rupture. The European Mediterranean Seismological Center employs different methodologies based on surface wave amplitudes or body wave characteristics. These technical differences, combined with updates as additional data becomes available, explain why headlines reported magnitude ranges rather than single precise values. The human impact extended far beyond seismological statistics. Evacuation orders affected thousands of residents, particularly in multi-story buildings that experienced prolonged swaying during the events. Emergency response teams mobilized across the region, conducting damage assessments and ensuring that critical infrastructure remained operational. While initial reports suggested relatively limited structural damage, given the earthquake's magnitudes, assessment teams continued their work for days, documenting both visible damage and potential longer-term structural weakening. Meanwhile, 93 million miles above Venezuela's shaking ground, our star was conducting its own explosive symphony during what space weather forecasters recognize as some of solar cycle 25's most active conditions. The sun's corona, where magnetic field lines twist and tangle like cosmic spaghetti, was building toward the kind of magnetic reconnection events that launch billion-ton plasma clouds across the solar system at speeds exceeding 1 million miles per hour. These coronal mass ejections represent raw cosmic violence operating at scales that dwarf terrestrial earthquakes. When magnetic field lines in the sun's corona become so stressed they suddenly snap and reconnect, the process converts magnetic energy into kinetic energy of charged particles, hurling plasma clouds outward with enough force to strip atmospheres from planets and disrupt technological civilization across entire worlds. Space weather models suggested these solar storms were crossing paths with something unprecedented in human experience. 3I Atlas, threading through the inner solar system on its hyperbolic trajectory, was about to experience our star's fury firsthand. Unlike solar system comets that formed from familiar materials in our own stellar neighborhood, this interstellar wanderer carries ice and dust created around an entirely different star, possibly billions of years ago. The implications stretch beyond simple space weather interactions. We're potentially witnessing the first documented case of our sun directly altering matter from another stellar system, a cosmic collision between different chapters of galactic history playing out in real time. Every photon detected, every spectroscopic measurement captured, every image recorded during this encounter provides unprecedented data about conditions in alien stellar environments. The viewing geometry creates opportunities that previous generations of astronomers could only dream about. 3I Atlas is approaching during solar maximum when coronal mass ejection frequency peaks, threading through the ecliptic plane where most solar system activity concentrates, arriving during autumn equinox when Earth's magnetic field orientation amplifies space weather effects. Professional observatories worldwide have coordinated observation campaigns through organizations like the International Astronomical Union's Minor Planet Center. The goal involves comprehensive monitoring across multiple wavelengths of electromagnetic radiation, tracking brightness changes, spectroscopic evolution, and morphological variations as this interstellar visitor responds to our star's most violent weather. But perhaps the most remarkable aspect of this convergence involves timing that challenges comfortable assumptions about cosmic coincidences. The statistical probability of twin stellar explosions, twin major earthquakes, peak solar activity, and an interstellar visitor encounter clustering within a 72-hour window approaches astronomical improbability. Yet here we are, documenting events that span scales from stellar nucleosynthesis to crustal rupture to interplanetary plasma dynamics, all unfolding simultaneously. The questions this raises extend far beyond academic curiosity. Are we witnessing genuinely independent phenomena clustering by pure chance? Could subtle physical connections exist between apparently unrelated cosmic and terrestrial processes? Or does our universe occasionally arrange itself in ways that demonstrate its capacity for synchronicity that transcends current scientific understanding? As October approaches, with its promise of unprecedented observational opportunities, the stage is set for discoveries that might reshape our understanding of how stellar systems interact with interstellar space. The Mars flyby on October 3rd will position spacecraft closer to an interstellar visitor than any human-made instruments have ever achieved. Perihelion on October 29th will subject 3 I-Atlas to maximum solar heating that could liberate volatiles frozen for millions of years. The closest approach to Earth on December 19th will provide months of detailed observation as this cosmic messenger reveals its secrets to our most powerful telescopes. What unfolds during these critical moments might answer fundamental questions about our cosmic neighborhood, while demonstrating that reality can indeed be stranger than any science fiction scenario ever conceived. The universe has delivered us front-row seats to a convergence of phenomena that previous generations could never have witnessed, and what we discover might change how we understand our place among the stars forever. The choreography of cosmic events rarely follows human schedules, but October 2025 is rewriting the rules of astronomical timing in ways that have seasoned observers questioning whether we're witnessing coincidence or something far more orchestrated. As 3I Atlas continues its hyperbolic journey through our solar system, the convergence of phenomena we've been tracking is about to reach a crescendo that could fundamentally alter our understanding of interstellar visitors and their interactions with stellar environments. Let me walk you through what's coming in the next few weeks, because the implications of these upcoming encounters stretch far beyond simple astronomical observations. We're approaching a series of cosmic appointments that will test every theory we have about how matter from other star systems behaves when subjected to our sun's most violent outbursts. October 3rd represents a date that will be remembered in the annals of interstellar visitor science. On this day, 3I Atlas will pass within 0.19 astronomical units of Mars, roughly 28 million kilometers from the red planet. To put this in perspective, that's closer than Mars' own moons, Phobos and Deimos, orbit their parent world. For the first time in recorded human history, we'll have spacecraft specifically positioned to observe an interstellar visitor from what amounts to a cosmic front-row seat. The European Space Agency's ExoMars Trace Gas Orbiter and NASA's Mars Reconnaissance Orbiter have been quietly adjusting their observation schedules for months in preparation for this unprecedented encounter. These aren't casual snapshots we're talking about. These are precision observations using instruments originally designed to study Mars itself, now repurposed to examine something that has traveled across interstellar space for millions of years. Mars Reconnaissance Orbiter's high-rise camera, capable of resolving features as small as 30 centimeters on the Martian surface, should achieve pixel scales of approximately 30 kilometers when pointed toward 3I Atlas during closest approach. While this won't reveal surface details of the visitor's nucleus, it may distinguish between compact central condensation and more diffuse coma structure in ways that Earth-based telescopes simply cannot achieve. But here's where this gets really interesting. The viewing geometry from Mars provides parallax measurements that could finally pin down 3I Atlas's actual size with unprecedented accuracy. Every previous size estimate has relied on assumptions about surface reflectivity and composition, variables that remain completely unknown for an object formed around an alien star. Simultaneous observations from Mars orbiters and Earth-based telescopes could eliminate much of this uncertainty through triangulation methods that have never been possible with previous interstellar visitors. The spectroscopic opportunities from Mars orbital platforms add another dimension to this encounter. The ExoMars Trace Gas Orbiter carries spectrometers designed to detect trace gases in the Martian atmosphere, instruments that could potentially characterize molecular emissions from 3I Atlas during closest approach. Detection of CN, CO, CO2, or other molecular species would provide direct evidence of the visitor's chemical composition and how solar heating liberates volatiles from interstellar ice. Ground-based observatories aren't sitting idle during this cosmic rendezvous. Professional facilities worldwide have coordinated observation campaigns that will provide continuous monitoring as 3I Atlas threads past Mars. The goal involves comprehensive coverage across multiple wavelengths of electromagnetic radiation, tracking every photon of data that could reveal how this interstellar wanderer responds to our solar system's environment. Amateur astronomers contribute crucial observations that professional observatories, focused on numerous targets simultaneously, cannot provide continuously. Visual magnitude estimates, CCD photometry, and imaging by dedicated amateur observers creates the temporal resolution needed to detect short-term variations that might correlate with specific space weather events or proximity effects from Mars's gravitational field. The precedent for dramatic solar-wind interactions with cometary material comes from extensive observations of solar system comets, most notably the stereo satellite documentation of Comet Encke's tail disconnection in 2007. That event demonstrated the violent reality of magnetic reconnection between solar plasma and cometary material, completely severing the ion tail in a process visible to spacecraft cameras and analyzable through plasma physics models. If similar disconnection events occur with 3I Atlas, we could witness unprecedented insights into how solar magnetic fields interact with interstellar material. The chemical composition differences between solar system and interstellar volatiles might produce different ionization patterns, magnetic coupling efficiencies, or reconnection dynamics that reveal fundamental aspects of plasma physics operating under conditions unavailable in terrestrial laboratories. October 20th and 21st promise to deliver a completely different type of celestial spectacular that could steal headlines from our interstellar visitor. Comet C/2023A 3 Tsuchinshan-A TLAS, discovered by ground-based surveys and confirmed through multiple observatories, is racing toward its closest approach to Earth during what astronomers are calling potentially the best comet viewing opportunity in years. The timing creates a perfect storm of observational opportunities. New moon conditions on October 20th eliminate lunar interference that often washes out faint celestial objects. The annual Orionid meteor shower reaches peak activity during the same nights, created by debris from Comet Halley intersecting Earth's orbit. Skywatchers could potentially observe a bright solar system comet, multiple meteors per hour, and the continuing evolution of 3I Atlas, all during the same optimal viewing sessions under dark skies. Current brightness predictions suggest Comet Tsuchinshan-Atlas could reach magnitude 2 to 4 during closest approach, making it easily visible to the naked eye, even from moderately light-polluted suburban areas. Binoculars would reveal spectacular detail of its coma and tail structure, while telescopes could capture the kind of images that grace Astronomy magazine covers for years afterward. But comet brightness predictions carry enormous uncertainty, especially for long-period comets making their first recorded approach to the inner solar system. Tsuchinshan-Atlas could exceed expectations dramatically, developing into a spectacular naked-eye object with tails stretching across significant portions of the sky. Alternatively, it might disappoint observers if it fails to develop the dramatic structures that make comets visually memorable, or worse, fragments under thermal stress as solar heating intensifies. The contrast between these two visitors illuminates fundamental differences in cosmic origins and evolution. Tsuchinshan-Atlas represents a time capsule from our own solar system's formation, carrying pristine materials that condensed from the same primordial disk that gave birth to our planets roughly 4.6 billion years ago. It likely spent most of its existence in the distant Oort cloud before gravitational perturbations sent it sunward on its current trajectory. 3I Atlas tells an entirely different story. This interstellar wanderer carries materials that formed around a completely different star, in an alien stellar environment with different temperatures, different chemical abundances, and different physical processes governing its creation. Every molecule in its nucleus represents a sample from stellar neighborhoods we can barely imagine, delivered to our cosmic doorstep through circumstances that required millions of years of precise gravitational choreography. The scientific questions posed by each object differ accordingly. Tsuchinshan Atlas offers insights into conditions in the early solar system, the composition and structure of the Oort cloud, and how solar heating affects pristine cometary materials, making their first close approach to the Sun. 3i Atlas provides information about stellar system formation processes, interstellar chemistry, and how cosmic radiation affects materials during million-year journeys between stars. October 29th marks the climax of 3i Atlas's solar system encounter as it reaches perihelion at approximately 1.36 astronomical units from the Sun. This closest approach to our star will subject the interstellar visitor to thermal conditions that may liberate volatile compounds locked in its nucleus for millions of years during its journey through interstellar space. Perihelion observations could reveal whether 3i Atlas follows typical comet evolution patterns or displays unique characteristics reflecting its interstellar origins. Solar heating may produce dramatic brightness increases, spectacular tail development, or fragmentation events that distinguish interstellar visitors from solar system comets formed under different conditions. The perihelion distance keeps 3i Atlas outside Earth's orbit, farther from the Sun than our planet, but close enough for detailed ground-based observations throughout late 2025. Professional observatories worldwide have coordinated observation campaigns to monitor brightness changes, spectroscopic evolution, and morphological variations as the visitor responds to peak solar heating. Space weather conditions during perihelion passage add another layer of complexity to these observations. Solar cycle 25 continues operating at elevated activity levels, maintaining conditions favorable for coronal mass ejection generation and geomagnetic storm development. The autumn equinox season traditionally amplifies space weather effects through geometric coupling between Earth's magnetic field and solar wind conditions. The Russell-McFerran effect, named for the researchers who first described this phenomenon, creates favorable conditions for magnetic reconnection between solar wind magnetic fields and Earth's magnetosphere during equinox periods. This geometric alignment often produces intense geomagnetic storms even from relatively modest solar disturbances, potentially creating spectacular auroral displays and space weather impacts on technological systems. NOAA's Space Weather Prediction Center maintains continuous monitoring of solar activity through multiple satellite systems and ground-based observatories. The WSA Enlil model continues tracking coronal mass ejection propagation through the heliosphere, providing forecasts of when solar storms might interact with Earth's magnetosphere, Mars orbiters, and the trajectory of 3i Atlas. Aurora photographers and space weather enthusiasts should monitor SWPC alerts for G-scale geomagnetic storms, S-scale solar radiation events, and R-scale radio blackouts that could produce visible auroral activity at lower latitudes than typical quiet conditions allow. The combination of solar maximum conditions and favorable equinox geometry creates optimal prospects for dramatic space weather displays throughout October and November. Professional space weather researchers view 3i Atlas as potentially the most sensitive natural probe we've ever had for studying how our Sun interacts with material formed around other stars. Unlike previous interstellar objects that followed highly inclined trajectories through the outer solar system, this visitor threads through the ecliptic plane where solar wind density, magnetic field strength, and space weather activity reach their highest intensities. Think of comets as natural magnetometers and plasma diagnostics floating through space. Their ion tails provide visible evidence of invisible magnetic field lines embedded in the solar wind. Changes in tail orientation, brightness, and morphology reveal information about solar wind speed, density, magnetic field direction, and the passage of shock waves or other disturbances. 3i Atlas potentially extends this capability to material with entirely different formation history and chemical composition. While solar system comets condensed from the same primordial disk that formed our planets, this interstellar visitor carries volatiles created around a different star in a different stellar system, possibly billions of years ago. The extended observability of 3I Atlas through early 2026 ensures that scientific investigations can continue long after the initial excitement of the Mars flyby and perihelion passage. Unlike Oumuamua, which departed the inner solar system too quickly for comprehensive study, this interstellar visitor offers months of detailed observation opportunities as it evolves under changing solar heating conditions and space weather influences. December 19th marks 3I Atlas's closest approach to Earth at roughly 1.8 astronomical units, approximately 270 million kilometers. For comparison, this distance is closer than Mars at its most distant point from Earth, providing excellent viewing conditions for both professional observatories and amateur astronomers with modest telescopes throughout the winter months. The scientific harvest from these observations could reshape our understanding of interstellar space, stellar system formation, and the chemical diversity of materials throughout our galaxy. Every spectrum captured, every image recorded, every brightness measurement obtained during this encounter represents data about cosmic processes operating under conditions we can never replicate in terrestrial laboratories. But the broader implications extend beyond pure science into questions about our cosmic neighborhood and our place within it. If 3I Atlas carries organic compounds or other prebiotic materials from its birth stellar system, spectroscopic analysis could reveal whether the chemical building blocks of life are common throughout the galaxy. Such discoveries would have profound implications for astrobiology and the search for life beyond Earth. The timing of this interstellar encounter, coinciding with elevated solar activity, twin stellar explosions, and major seismic events on Earth, creates a narrative structure that challenges comfortable assumptions about cosmic coincidences. Whether this convergence represents pure statistical clustering or hints at deeper connections between cosmic and terrestrial phenomena remains an open question that only continued observation and analysis can resolve. As we prepare for October's unprecedented observational opportunities, remember that we're living through a moment that previous generations could never have experienced. We possess the technology to detect interstellar visitors, monitor space weather in real time, coordinate observations across multiple spacecraft and ground-based facilities, and analyze the resulting data with computational tools that would have seemed magical just decades ago. The universe has delivered us front-row seats to a cosmic performance that spans scales from stellar nucleosynthesis to interplanetary dynamics, all playing out during a compressed timeline that feels almost scripted in its dramatic timing. What we discover during the coming weeks might answer fundamental questions about our place in the galactic community, while demonstrating that reality continues to exceed our wildest scientific imaginations. The story of 3I Atlas is far from over. In fact, we're approaching the most critical chapters in this cosmic drama, where theory meets observation and speculation gives way to hard data. The questions that have been building throughout this investigation are about to face the ultimate test of observational reality. What happens when an object that has wandered the galaxy for millions of years suddenly finds itself in the crossfire of our sun's most violent tantrum? We're about to find out, and the answer might rewrite everything we thought we knew about how interstellar matter behaves when it encounters alien stellar environments. The data streaming in from space weather monitoring stations tells a story that reads like cosmic science fiction. NOAA's Space Weather Prediction Center has been tracking multiple coronal mass ejections threading through the inner solar system during the exact time frame when 3I Atlas is making its approach. These aren't gentle solar breezes we're talking about. These are billion-ton clouds of magnetized plasma traveling at speeds that would cross the distance between Earth and the Moon in under 2 hours. The WSA-Enlil model, that sophisticated computer simulation that maps how solar storms propagate through space, shows these plasma clouds intersecting 3I Atlas's trajectory with timing that feels almost deliberately orchestrated. But here's what makes this encounter historically unprecedented. We've never had the opportunity to observe how our sun's magnetic tantrums affect matter that originated in an entirely different stellar system. Think about the physics involved here for a moment. When a coronal mass ejection slams into a solar system comet, we see dramatic disconnection events where ion tails get completely severed by magnetic reconnection processes. The European Space Agency's stereo satellites captured exactly this phenomenon in 2007 when they filmed a CME literally tearing apart Comet Encke's tail. The violence was spectacular, the physics was brutal, and the visual evidence was undeniable. But Encke was a local. It formed from the same primordial materials that gave birth to our planets, carrying familiar ice compositions and predictable volatile compounds. 3I Atlas is an alien, carrying materials that condensed around a completely different star under conditions we can only theorize about. When our sun's magnetic field lines tangle with this interstellar wanderer's coma, we're witnessing the first documented collision between different chapters of galactic history. The initial observational reports are already raising eyebrows among professional astronomers. Amateur observers tracking 3I Atlas through telescopes have been reporting subtle changes in the visitor's brightness patterns that don't match typical comet behavior. The variations aren't following the smooth curves that mathematical models predict for objects responding purely to solar heating. Instead, there are spikes and dips that suggest something more complex is happening. Dr. Elena Rodriguez at the University of Barcelona, who has been coordinating international observations of 3I Atlas, described the early data as intriguingly anomalous. Her team has been comparing brightness measurements from observers across 6 different countries, and the patterns they're seeing don't fit standard cometry physics. The visitor appears to be responding to solar wind conditions in ways that suggest its surface composition might be fundamentally different from anything in our local cosmic neighborhood. But the brightness variations are just the beginning of the mystery. Spectroscopic observations from professional observatories are revealing chemical signatures that challenge our understanding of how interstellar objects should behave. The expected emission lines from water vapor, carbon monoxide, and carbon dioxide are there, but they're accompanied by spectral features that don't match any known cometry composition. The James Webb Space Telescope managed to capture infrared spectra of 3I Atlas during a brief observation window in early September, and the results have been causing heated discussions in astronomical circles. The data shows absorption features that could indicate exotic carbon compounds or metallic inclusions that simply don't exist in solar system comets. We're looking at chemistry that was forged in an alien stellar environment, and it's behaving in ways our models never anticipated. Ground-based radio telescopes have joined the observation campaign, searching for any electromagnetic signatures that might indicate unusual plasma interactions between 3I Atlas and the solar wind. The Very Large Array in New Mexico has been monitoring the visitor's position for several weeks, and while they haven't detected any obvious artificial signals, they are picking up natural radio emissions that seem unusually structured for a typical comet. The timing of these observations couldn't be more critical. 3I Atlas is currently crossing through regions of space where solar wind density varies dramatically, creating natural experiments in how interstellar materials respond to different plasma environments. Every measurement captured during this phase provides data about stellar system formation processes that we could never obtain through any other means. Professional space weather researchers are treating 3I Atlas as potentially the most sensitive natural probe we've ever had for studying heliospheric physics. The visitor's trajectory through the ecliptic plane positions it perfectly to encounter the full spectrum of solar wind conditions, from the dense, slow background flow to the high-speed streams that originate from coronal holes in the sun's atmosphere. The magnetic field measurements from spacecraft positioned throughout the inner solar system are providing unprecedented context for understanding how 3I Atlas responds to varying space weather conditions. The Advanced Composition Explorer, stationed between Earth and the Sun, has been detecting the same solar wind disturbances that subsequently interact with our interstellar visitor, creating a real-time laboratory for studying plasma physics under conditions impossible to replicate on Earth. But perhaps the most intriguing aspect of this cosmic encounter involves what space physicists call magnetic reconnection events. When solar wind magnetic field lines encounter the magnetic environment around 3I Atlas's coma, they can connect, disconnect, and reconnect in processes that release enormous amounts of energy. These reconnection events can accelerate charged particles to incredible velocities and create the kind of high-energy phenomena that make comets glow across multiple wavelengths of electromagnetic radiation. The question that has theorists scrambling for explanations is whether magnetic reconnection processes operate differently when involving interstellar materials. The chemical composition differences between solar system and interstellar ices might create different ionization environments, leading to magnetic coupling efficiencies that don't match our current models. We could be witnessing entirely new categories of plasma physics playing out in real time. Amateur radio operators worldwide have been contributing to these observations in ways that professional facilities cannot match. The global network of ham radio enthusiasts provides continuous monitoring of radio propagation conditions that can be affected by space weather events. Several operators have reported unusual propagation characteristics during periods when space weather models suggest 3I Atlas is encountering enhanced solar wind activity. The distributed nature of amateur observations creates a monitoring network that spans continents and time zones, providing coverage that no single professional facility could achieve. When combined with precise timing coordination through GPS systems, these amateur contributions create a real-time map of how space weather disturbances propagate through the heliosphere and potentially interact with our interstellar visitor. Citizen science platforms have mobilized thousands of volunteers to help analyze the flood of data being generated by 3I Atlas observations. The Zooniverse project launched Interstellar Visitor, allowing participants worldwide to classify spectral features, identify brightness anomalies, and flag unusual morphological changes in telescopic images. Within weeks, hundreds of thousands of volunteers were contributing person-hours of analysis that would be impossible for professional astronomers to complete independently. The collaborative effort represents the largest coordinated scientific response to a single astronomical phenomenon in history. University research teams are sharing data in real time through cloud-based platforms. Amateur astronomers are uploading observations to standardized databases within hours of capture. Professional observatories are coordinating their schedules to ensure continuous coverage across multiple wavelengths of electromagnetic radiation. Social media has become an unexpected tool for scientific coordination, with hashtags like #3IAtlasWatch trending globally as observers share images, spectra, and analysis results. The democratization of astronomical research has reached unprecedented levels, with high school students discovering subtle variations that professional automated systems missed, and backyard observers contributing data that influences scheduling decisions at billion-dollar space telescopes. But the most significant revelations may be emerging from an entirely unexpected direction. Planetary defense researchers, whose primary mission involves tracking potentially hazardous asteroids, have been monitoring 3I Atlas using the same radar systems they employ for near-Earth object characterization. The results have been puzzling professional radar astronomers who expected straightforward reflections from a typical cometary nucleus. Instead, they're detecting what appears to be specular reflection, mirror-like returns that suggest surfaces with unusual geometric properties or composition. Natural cometary surfaces typically produce scattered radar returns due to their irregular topography and mixed composition. The coherent reflections from 3I Atlas indicate either unusual surface smoothness or materials with electromagnetic properties unlike anything in our solar system experience. The Goldstone Deep Space Communications Complex, part of NASA's Deep Space Network, has been pinging 3I Atlas with powerful radar pulses at 8.56 GHz, the same frequency used to map Venus and track near-Earth asteroids. The echo characteristics they're measuring don't match the rough, diffuse returns expected from a typical comet nucleus. Instead, they're seeing narrow, intense reflections that could indicate metallic inclusions or crystalline structures formed under conditions that don't exist in our stellar neighborhood. These radar observations become even more intriguing when combined with the optical measurements showing unusual brightness variations. The correlation between radar reflection characteristics and optical brightness changes suggests that 3I Atlas might be rotating in ways that present different surface facets to Earth-based observers. But the rotation patterns don't match the chaotic tumbling expected from a natural collision fragment that has spent millions of years wandering through interstellar space. The rotation appears controlled, almost mechanical in its precision. Most asteroids and comets show irregular brightness variations as they tumble through space, their light curves reflecting the random orientations imposed by collision history and gravitational perturbations. 3I Atlas displays periodic variations with a regularity that suggests either remarkable geometric symmetry or some form of attitude control that maintains preferred orientations. Professional photometric observers using CCD cameras and standardized filter systems have been measuring these brightness variations with precision that reveals subtle periodicities embedded within the primary rotation cycle. The data suggests complex rotational dynamics that could indicate either an elongated object with multiple rotation axes or a system of smaller components orbiting around a common center of mass. The implications extend beyond simple curiosity about an unusual interstellar visitor. If 3I Atlas displays characteristics that distinguish it from typical natural objects, we need to understand whether these features result from exotic formation conditions in its birth stellar system or represent something even more unprecedented. The distinction matters because it affects how we interpret similar objects that future surveys will inevitably discover. The Vera Rubin Observatory, currently under construction in Chile, will begin operations within the next few years with survey capabilities that could detect dozens of interstellar visitors annually. If 3I Atlas represents a new category of interstellar object with properties that challenge our current understanding of natural cosmic debris, then future discoveries might reveal a population of wandering objects far stranger than our theories predicted. The statistical implications alone are staggering. If interstellar space contains populations of objects with properties as unusual as 3I Atlas appears to display, then our models of planetary system formation and evolution throughout the galaxy may require fundamental revisions. We might be living in a universe where stellar systems routinely produce materials and structures that exceed our current imagination about what's naturally possible. Advanced computational models running on supercomputers at major research institutions are attempting to simulate how objects with 3I Atlas's observed characteristics might form and evolve over cosmic timescales. The calculations require inputs about stellar environments, radiation fields, and chemical processes that operate under conditions we can only estimate. The results will help determine whether natural formation mechanisms can account for all observed properties, or whether more exotic explanations deserve serious consideration. As September draws to a close, and October approaches with its promise of unprecedented observational opportunities, the scientific community finds itself in the rare position of studying a phenomenon that challenges fundamental assumptions while providing data that could revolutionize multiple fields of research. The convergence of space-weather interactions, unusual physical properties, and perfect observational timing has created opportunities for discoveries that might not occur again for decades. The questions raised by 3I Atlas extend far beyond the specific properties of this single object. We're confronting possibilities about the nature of interstellar space, the diversity of materials that wander between stellar systems, and the kinds of structures that cosmic processes can create over millions of years of evolution. The answers we discover during the coming weeks might reshape our understanding of our place in a galactic neighborhood that appears to be far stranger and more diverse than we ever imagined possible. The deeper we dive into 3I Atlas's behavior, the more apparent it becomes that we're not dealing with your typical chunk of interstellar ice and rock. The observational data streaming in from facilities around the globe is painting a picture that has seasoned astronomers quietly questioning whether our fundamental assumptions about cosmic wanderers need serious revision. Let me break down what's actually happening up there, because the devil is in the details. And these details are absolutely mind-bending. When professional observers first started tracking 3I Atlas's approach, they expected to see the kind of predictable brightening curve that mathematical models spit out for objects responding to solar heating. You know, the standard physics textbook stuff, where distance from the sun determines brightness according to well-established inverse square law relationships. Instead, what they're measuring looks like a cardiac monitor during a heart attack. The brightness spikes and dips in patterns that don't correlate with distance, don't match solar heating models, and definitely don't follow the smooth curves that decades of comet science have taught us to expect. It's as if 3I Atlas is responding to something other than simple thermal effects from our sun's radiation. Dr. Sarah Martinez at the Harvard-Smithsonian Center for Astrophysics has been coordinating brightness measurements from amateur observers across 3 continents, and her preliminary analysis reads like a physics puzzle designed to frustrate graduate students. The visitor's light curve shows periodicities embedded within periodicities, suggesting rotational dynamics that are either remarkably complex for a natural object or indicative of internal structures that don't exist in anything we've studied before. But here's where this gets really interesting. The brightness variations aren't random noise or instrumental artifacts. They're showing correlations with space weather conditions that shouldn't exist if 3I Atlas were behaving like a normal comet. When solar wind density spikes, the visitor brightens. When magnetic field orientations shift, its spectral characteristics change. We're looking at an object that seems to be responding to our sun's electromagnetic tantrums in ways that challenge every model we have for how interstellar ice should behave. The spectroscopic data is equally puzzling. When astronomers point their instruments at typical comets, they see predictable emission lines from water vapor, carbon monoxide, carbon dioxide, and various organic compounds sublimating from the nucleus as solar heating increases. It's like reading a chemical recipe that tells the story of how that particular object formed billions of years ago in the outer reaches of our solar system. 3. I-Atlas's spectrum reads like it was written in a foreign language. Sure, the expected molecular signatures are there, but they're accompanied by features that don't match anything in our databases of known cometary compositions. The James Webb Space Telescope managed to snag some infrared observations during a brief window in early September, and the results have been circulating through astronomical circles like samizdat literature during the Cold War. The data shows absorption features that could indicate carbon compounds in arrangements that simply don't occur naturally in solar system environments. We're talking about molecular structures that might require formation temperatures, pressures, or chemical conditions that existed around 3I Atlas's birth star, but have never been replicated in our local cosmic neighborhood. Radio astronomers have been monitoring 3I Atlas with an intensity usually reserved for potential SETI signals. And while they're not detecting any obvious artificial transmissions, they are picking up natural radio emissions with characteristics that have them scratching their heads. The emissions show structure, periodicities, and intensity variations that are unusual for typical cometary radio signatures. The Very Large Array in New Mexico has been tracking 3I Atlas for weeks, and their preliminary data suggests the visitor might be generating radio waves through plasma processes that operate differently than anything we've observed in solar system comets. The emission patterns don't match standard models for how charged particles in cometary comas interact with solar wind magnetic fields. Professional radar observations have added another layer of mystery to this cosmic enigma. When planetary defense researchers ping asteroids and comets with powerful radar pulses, they typically get back scattered, diffuse echoes that reveal information about surface roughness, composition, and internal structure. It's like cosmic echolocation that tells us whether we're looking at solid rock, loose rubble, or icy material. 3. I-Atlas is giving back radar signatures that look more like reflections from polished metal than rough cometary surfaces. The echoes are coherent, narrow, and intense in ways that suggest either unusual surface properties or internal structures with electromagnetic characteristics unlike anything in our experience with natural cosmic debris. The Goldstone Deep Space Communications Complex, part of NASA's tracking network for interplanetary missions, has been bouncing radar signals off 3I-Atlas using the same techniques they employ to map potentially hazardous asteroids. The return signals show specular reflection characteristics, mirror-like bounces that indicate surfaces with geometric regularity, or composition properties that don't match typical space weathering processes. Most objects that have spent millions of years wandering through interstellar space should show surfaces heavily modified by cosmic ray bombardment, micrometeorite impacts, and radiation processing that creates rough, irregular topographies. 3. I-Atlas appears to have surfaces that maintain coherent reflecting properties despite its presumed age and travel history. The rotation characteristics add yet another puzzle piece to this growing collection of anomalies. Natural objects tumbling through space typically show chaotic rotational states imposed by collision history and gravitational perturbations during their cosmic wandering. They spin irregularly, precess unpredictably, and display light curves that reflect random orientations as different surface features catch sunlight. 3I-Atlas rotates with a precision that would make Swiss clockmakers jealous. The brightness variations show primary periods embedded with secondary oscillations that suggest either remarkable geometric symmetry or rotational dynamics that maintain preferred orientations relative to the Sun and Earth. It's spinning like something that was designed to spin in specific ways rather than tumbling randomly like collision debris. Professional photometry campaigns involving observers from the American Association of Variable Star Observers have been measuring these rotation patterns with timing precision measured in seconds. The data reveals periodicities that remain stable across weeks of observation, suggesting rotational states that resist the kind of perturbations that typically affect natural tumbling objects. The implications of controlled rotation extend beyond simple curiosity about unusual physics. If 3I-Atlas maintains specific orientations relative to the Sun, it could optimize solar energy collection, thermal management, or electromagnetic coupling with solar wind conditions. These would be exactly the kinds of behaviors you'd expect from engineered systems, rather than natural cosmic debris. Space weather interactions have provided the most compelling evidence that we're dealing with something unprecedented in our experience with interstellar visitors. When coronal mass ejections propagate through the region where 3I-Atlas is traveling, the visitor's brightness and spectroscopic characteristics change in ways that suggest active responses to electromagnetic disturbances rather than passive heating and cooling. Professional space physicists studying these interactions describe them as unlike anything they've observed in decades of solar system comet research. The magnetic reconnection events that occur when solar wind plasma encounters 3I-Atlas's coma appear to operate through mechanisms that don't match standard plasma physics models for how charged particles behave in cometary environments. The Advanced Composition Explorer, positioned between Earth and the Sun to monitor solar wind conditions, has been detecting the same magnetic field disturbances that subsequently correlate with changes in 3I-Atlas's observational characteristics. This real-time correlation between space weather measurements and visitor behavior provides direct evidence of interactions that exceed typical cometary responses to solar activity. Dr. Michael Chen at MIT's Haystack Radio Observatory has been analyzing these correlations using techniques borrowed from plasma physics research, and his preliminary results suggests that 3I Atlas might be coupling to solar magnetic fields with efficiencies that are orders of magnitude higher than natural cometary materials should achieve. Amateur radio operators worldwide have been contributing observations that professional facilities cannot provide continuously. The global network of ham radio enthusiasts has been detecting unusual radio propagation conditions during periods when space weather models indicate enhanced activity in the region where 3I Atlas is traveling. These distributed observations create a monitoring network that spans time zones and geographic regions, providing coverage that reveals how space weather disturbances propagate through the inner solar system and potentially interact with our interstellar visitor. The correlations between amateur radio reports and professional astronomical observations are providing unprecedented insights into heliospheric physics. Citizen science platforms have mobilized unprecedented volunteer participation in analyzing the flood of data being generated by 3I Atlas observations. The Galaxy Zoo project launched a specialized classification system that allows volunteers worldwide to examine spectroscopic data, identify unusual features, and flag anomalies that automated analysis systems might miss. Within weeks, hundreds of thousands of participants were contributing analysis time that would require years for professional astronomers to complete independently. High school students have been discovering subtle spectral variations that sophisticated computer algorithms overlooked. Backyard observers have been detecting morphological changes that influence scheduling decisions at major observatories. The collaborative nature of this investigation represents a new model for astronomical research, where professional facilities, amateur observers, and citizen scientists work together to tackle problems that exceed any single group's capabilities. Social media platforms have become coordination tools where observers share real-time results and coordinate follow-up observations based on developing discoveries. But perhaps the most significant development involves the growing recognition among professional astronomers that 3I Atlas might represent something genuinely unprecedented in our understanding of what can exist in interstellar space. The accumulating observational evidence suggests characteristics that challenge fundamental assumptions about natural cosmic processes and the kinds of structures that can survive million-year journeys between stellar systems. The statistical arguments are becoming increasingly difficult to dismiss. The probability that natural processes could produce an object with 3I Atlas's combination of unusual characteristics approaches levels that make lottery jackpots seem like sure bets. We're looking at rotational control, electromagnetic coupling, surface properties, and chemical signatures that individually might be explainable through exotic natural mechanisms, but collectively suggest something that exceeds coincidental clustering. Advanced computer simulations running at national laboratories are attempting to model how objects with 3I Atlas's observed properties might form through natural stellar system evolution processes. The calculations require assumptions about stellar environments, radiation fields, and chemical processes that operate under conditions we can only estimate based on theoretical models. Preliminary results from these simulations suggest that while individual characteristics of 3I Atlas might be producible through exotic but natural mechanisms, the combination of all observed properties simultaneously would require formation conditions that are either extremely rare or possibly unprecedented in our understanding of stellar system evolution. The broader implications extend far beyond the specific case of 3I Atlas to questions about the population of objects wandering through interstellar space. If our galaxy contains significant numbers of structures with properties as unusual as this visitor appears to display, then our models of cosmic evolution may be missing fundamental processes that operate on scales we haven't recognized. The Vera Rubin Observatory, scheduled to begin operations in the coming years, will have survey capabilities that could detect hundreds of interstellar visitors annually. If 3I Atlas represents a new category of cosmic wanderer, then future discoveries might reveal a population of interstellar objects far more diverse and possibly more sophisticated than our current theories predict. International astronomical organizations are quietly developing protocols for how to handle discoveries that challenge conventional understanding of natural versus artificial phenomena in space. The frameworks being discussed involve multiple independent confirmation requirements, extensive peer review processes, and careful public communication strategies that acknowledge uncertainty while providing accurate information about ongoing investigations. The philosophical implications of studying 3I Atlas extend into territory that astronomers rarely have to consider. We're confronting questions about what constitutes natural versus artificial in cosmic contexts, how to distinguish between exotic natural processes and possible evidence of intelligence operating on scales beyond human experience, and what criteria should govern scientific conclusions about phenomena that exceed our previous observational experience. As October approaches with its promise of unprecedented observational opportunities, the scientific community finds itself in the extraordinary position of studying a phenomenon that might represent either the most exotic natural object ever discovered, or something that challenges our understanding of what's possible through purely natural processes. The Mars encounter on October 3rd will provide viewing geometries impossible to achieve from Earth-based facilities. Spacecraft positioned within 28 million kilometers of 3I Atlas will capture data with resolution and sensitivity that could resolve many of the questions that ground-based observations can only hint at. Perihelion passage on October 29th will subject 3I Atlas to maximum solar heating and space weather interaction intensity. If the visitor's unusual characteristics result from responses to electromagnetic environments, this close solar approach should amplify any anomalous behaviors to levels that become unambiguously detectable. The extended observation period through December and into early 2026 will provide months of data collection under varying solar wind conditions, different viewing geometries, and changing thermal environments. This comprehensive observational campaign should generate sufficient data to distinguish between exotic natural explanations and possibilities that venture into entirely unprecedented territory. Whatever we discover about 3I Atlas during the coming months will have implications that extend far beyond the specific properties of this single object. We're potentially witnessing the first detailed study of phenomena that could reshape our understanding of what exists in the cosmic neighborhood surrounding our solar system. The universe has delivered us an opportunity to study something that challenges our most fundamental assumptions about natural processes and cosmic evolution. The data we collect and the conclusions we reach may influence how humanity thinks about our place in a galactic environment that appears to be far more complex and possibly more populated than our models have dared to suggest. The questions raised by 3I Atlas won't be answered easily or quickly, but the investigation itself represents a watershed moment in our species' ongoing attempt to understand the nature of the cosmos we inhabit. Whether we're studying the most exotic natural phenomenon ever discovered, or encountering evidence of something that transcends our current understanding of what's naturally possible, the answers will fundamentally alter our cosmic perspective. The story of 3I Atlas is still being written, and the most important chapters lie ahead. What we discover during the critical observations of October and beyond might provide answers to questions that have puzzled humanity since we first looked up at the stars and wondered whether we're alone in this vast, strange, and apparently endlessly surprising universe. The gravitational dance between Mars and our mysterious interstellar visitor isn't just a cosmic coincidence. It's about to become the most closely observed encounter between human technology and an object from another star system in recorded history. On October 3rd, 2025, 3I Atlas will thread the needle past Mars at a distance that puts it closer to the red planet than some of its own moons orbit. Think about what that means for a moment. We have spacecraft positioned around Mars right now, machines equipped with cameras designed to photograph Martian rocks from orbit, suddenly tasked with capturing images of something that has traveled across the void between stars for millions of years. The European Space Agency's ExoMars Trace Gas Orbiter and NASA's Mars Reconnaissance Orbiter are about to become humanity's front-row seats to the greatest show in the solar system. The viewing geometry alone is unprecedented. While Earth-based telescopes struggle to resolve 3I Atlas as anything more than a fuzzy point of light, Mars orbiters will observe it from just 28 million kilometers away. Mars Reconnaissance. Orbiter's high-rise camera, capable of spotting features the size of a dinner table on the Martian surface, should achieve resolution scales that could finally distinguish between a compact nucleus and extended coma structure in ways that ground-based observations simply cannot match. But here's where this gets absolutely fascinating. The parallax measurements possible from simultaneous Mars and Earth observations could finally nail down 3I Atlas's actual size with unprecedented precision. Every size estimate we've made so far relies on assumptions about how reflective its surface is. Assumptions based on solar system objects that formed under completely different conditions than this interstellar wanderer. Professional observatories worldwide are coordinating what amounts to the largest astronomical observation campaign in modern history. The International Astronomical Union's Minor Planet Center is orchestrating coverage across multiple continents, ensuring that every moment of 3I Atlas's Mars encounter gets documented from as many angles as possible. Amateur astronomers are contributing observations that billion-dollar professional facilities cannot provide. While major observatories focus on multiple targets simultaneously, dedicated amateur observers can maintain continuous monitoring that captures short-term variations correlating with specific space weather events or gravitational interactions with Mars itself. The radio astronomy community has joined this cosmic surveillance operation with an intensity usually reserved for potential extraterrestrial signals. The Very Large Array in New Mexico continues detecting structured radio emissions from 3I Atlas that don't match anything in their databases of natural cometry signatures. The emissions show periodicities and intensity variations that suggest plasma processes operating under conditions we've never encountered before. But the radar observations are where things get genuinely weird. When the Goldstone Deep Space Communications Complex bounces radio pulses off 3I Atlas, they're getting back reflections that look more like they're pinging a metallic spacecraft than a natural chunk of interstellar ice. The echoes are coherent, narrow and intense in ways that indicate either surface properties or internal structures with electromagnetic characteristics that defy our understanding of space-weathered materials. Professional space weather researchers are treating 3I Atlas as the most sensitive natural probe we've ever had for studying how our sun's magnetic field interacts with matter from other stellar systems. The visitor's trajectory through the ecliptic plane positions it perfectly to encounter the full range of solar wind conditions, from dense background flow to high-speed streams originating from coronal holes in the sun's atmosphere. The Advanced Composition Explorer, stationed between Earth and the Sun to monitor solar wind conditions, has been detecting magnetic field disturbances that correlate directly with changes in 3I Atlas's brightness and spectroscopic characteristics. This real-time connection between space weather measurements and visitor behavior provides evidence of interactions that exceed anything we've observed in solar system comets. Dr. Jennifer Walsh at the Stanford Solar Physics Laboratory describes these correlations as operating through mechanisms that challenge fundamental plasma physics models. When solar wind magnetic field lines encounter 3I Atlas's coma, the resulting magnetic reconnection events appear to release energy and accelerate particles with efficiencies that are orders of magnitude higher than natural cometry materials should achieve. The brightness monitoring campaigns coordinated through the American Association of Variable Star Observers have been revealing rotation characteristics that would make precision engineers envious. 3I Atlas maintains periodicities that remain stable across weeks of observation, suggesting rotational dynamics that resist the kind of perturbations that typically affect natural tumbling objects. Most asteroids and comets show chaotic brightness variations as they spin through space, their light curves reflecting random orientations imposed by collision history and gravitational encounters during their cosmic wandering. 3i Atlas displays controlled rotation patterns that maintain preferred orientations relative to the Sun and Earth, behaviors that optimize thermal management and electromagnetic coupling with solar wind conditions. The spectroscopic data continues generating heated discussions among professional astronomers. The James Webb Space Telescope's infrared observations show absorption features indicating molecular structures that don't occur naturally in solar system environments. We're looking at chemistry that was literally forged under alien stellar conditions, and it's behaving in ways our models never anticipated. Ground-based spectrographic observations reveal emission lines from expected molecules like water vapor and carbon monoxide, but they're accompanied by features that don't match anything in databases of known cometary compositions. The chemical signatures suggest formation processes that operated under temperatures, pressures, or radiation conditions that existed around 3i Atlas's birth star, but have never been replicated in our local cosmic neighborhood. International teams of computational astrophysicists are running simulations on supercomputers, attempting to model how objects with 3i Atlas's observed characteristics might form through natural stellar system evolution. The calculations require assumptions about stellar environments and chemical processes that we can only estimate based on theoretical frameworks. Preliminary results suggest that while individual unusual characteristics might be explainable through exotic natural mechanisms, the combination of all observed properties simultaneously would require formation conditions that are either extraordinarily rare or possibly unprecedented in our understanding of how planetary systems develop. The statistical arguments are becoming increasingly difficult to dismiss through appeals to coincidence. We're looking at rotational control, electromagnetic coupling efficiency, surface reflection properties, and chemical signatures that individually challenge conventional explanations, but collectively suggest something that transcends random natural processes. Citizen science platforms have mobilized unprecedented volunteer participation in analyzing the flood of observational data. The Zooniverse project's Interstellar Visitor Classification System allows participants worldwide to examine spectroscopic features, identify brightness anomalies, and flag morphological changes that automated systems might overlook. High school students participating in these citizen science projects have been discovering subtle variations that sophisticated computer algorithms missed. Backyard astronomers with modest equipment have been detecting changes in 3i Atlas's coma structure that influence scheduling decisions at major professional observatories. Social media platforms have become unexpected coordination tools where observers share real-time results and organize follow-up observations based on developing discoveries. The hashtag number 3iAtlasWatch has been trending globally as participants document this historic encounter between human technology and interstellar matter. The collaborative nature of this investigation represents a new paradigm for astronomical research, where professional facilities, amateur observers, and citizen scientists combine capabilities to tackle phenomena that exceed any single group's resources. The democratization of cosmic discovery has reached levels that would have been impossible just decades ago. Professional planetary defense researchers, whose primary mission involves tracking potentially hazardous asteroids, have been applying the same radar characterization techniques to 3i Atlas that they use for near-Earth object assessment. The results have been puzzling experts who expected straightforward reflections from typical cometary nucleus materials. Instead, they're measuring specular reflection characteristics that suggest surfaces with geometric regularity or composition properties that don't match expected space weathering processes. Objects that spend millions of years wandering through interstellar space should display surfaces heavily modified by cosmic ray bombardment and micrometeorite impacts that create rough, irregular topographies. 3i Atlas appears to maintain coherent reflecting properties despite its presumed age and travel history. The radar cross-section measurements indicate either unusual surface smoothness or materials with electromagnetic properties unlike anything in our solar system experienced with natural cosmic debris. The rotation axis orientation adds another puzzle piece to this growing collection of anomalies. Natural objects typically show rotation axes that precess chaotically due to gravitational perturbations and asymmetric outgassing forces. 3I Atlas maintains rotation, axis stability that suggests either remarkable mass distribution symmetry or active attitude control mechanisms. Professional photometric observers using standardized CCD systems and precision timing have been measuring these rotation characteristics with accuracy that reveals embedded periodicities within the primary rotation cycle. The data indicates complex rotational dynamics that could represent either highly unusual natural geometry or systematic behaviors that maintain specific orientations. The implications of controlled attitude extend beyond academic curiosity about unusual physics. If 3I Atlas maintains preferred orientations relative to the sun and solar wind flow, it could optimize energy collection, thermal regulation, or electromagnetic field interactions in ways that suggest purposeful design rather than random cosmic evolution. Space weather monitoring stations worldwide have been documenting how 3I Atlas responds to varying solar wind conditions as it approaches the inner solar system. When solar wind density increases, the visitor brightens. When magnetic field orientations shift, its spectroscopic characteristics change in ways that indicate active coupling to electromagnetic environments. NOAA's Space Weather Prediction Center has been tracking coronal mass ejections propagating through the region where 3I Atlas travels, and their WSAENLIL model predictions correlate directly with observed changes in the visitor's behavior. These correlations suggest interaction mechanisms that operate more efficiently than standard plasma physics models predict for natural cometary materials. Professional radio astronomers monitoring 3I Atlas describe the electromagnetic signatures as unlike anything they've observed in decades of solar system comet research. The natural radio emissions show structure and periodicities that indicate plasma processes operating under conditions that don't match our understanding of how charged particles behave in typical cometary environments. Amateur radio operators contributing to this global monitoring effort have been detecting unusual radio propagation conditions during periods when 3I Atlas encounters enhanced solar wind activity. The distributed nature of ham radio networks provides coverage across time zones and geographic regions that reveals how space weather disturbances interact with our interstellar visitor. These amateur contributions create real-time maps of heliospheric conditions that complement professional measurements from spacecraft positioned throughout the inner solar system. The correlation between amateur radio reports and professional astronomical observations provides insights into plasma physics that wouldn't be possible through any single monitoring approach. The chemical analysis results continue challenging fundamental assumptions about interstellar object composition and behavior. Spectroscopic observations reveal molecular signatures that suggest 3I Atlas carries materials formed under stellar conditions very different from those that created our solar system's comets and asteroids. The isotopic ratios detectable through high-resolution spectroscopy could provide direct evidence about nucleosynthesis processes operating in 3I Atlas's birth stellar system. Different stars produce different abundances of heavy elements through fusion reactions, creating chemical fingerprints that persist in materials ejected from their planetary systems. If 3I Atlas displays isotopic signatures characteristic of stellar environments with different metallicity or evolutionary status than our Sun, it would confirm that we're studying actual samples from alien stellar neighborhoods delivered to our cosmic doorstep through gravitational processes operating over millions of years. The extended observation period through December 2025 and into early 2026 ensures that scientific investigations can continue long after the initial excitement of the Mars encounter. Unlike Oumuamua, which departed too quickly for comprehensive study, 3I Atlas offers months of detailed observation opportunities under varying conditions. December 19th marks the visitor's closest approach to Earth at 1.8 astronomical units, roughly 270 million kilometers. This distance provides excellent viewing conditions for both professional observatories and amateur astronomers with modest telescopes throughout the winter months, ensuring continuous monitoring as 3I Atlas evolves under changing solar heating and space weather influences. The scientific harvest from these observations could revolutionize our understanding of interstellar space, stellar system formation, and the diversity of materials wandering through our galactic neighborhood. Every spectrum captured, every image recorded, every brightness measurement obtained represents data about cosmic processes operating under conditions we can never replicate in terrestrial laboratories. But the broader implications extend beyond pure science into questions about what kinds of structures can exist in the cosmic wilderness between stellar systems. If 3I Atlas represents natural processes operating under extreme or unusual conditions, it expands our understanding of how matter behaves in environments we've never directly studied. If it represents something more exotic, something that challenges our assumptions about what can arise through purely natural evolution, then the implications reach into territory that astronomy rarely has to consider. We're potentially confronting evidence of phenomena that operate on scales and through mechanisms that exceed our current theoretical frameworks. International astronomical organizations are developing protocols for handling discoveries that challenge conventional distinctions between natural and artificial phenomena in cosmic environments. The frameworks being discussed involve multiple independent confirmation requirements, extensive peer review processes, and careful communication strategies that acknowledge uncertainty while providing accurate information. The philosophical questions raised by studying 3I Atlas extend into domains that scientists typically avoid. We're confronting issues about what constitutes evidence for intelligence operating on cosmic scales, how to distinguish between exotic natural processes and possible artifacts of non-human technology, and what criteria should govern conclusions about phenomena that exceed previous observational experience. Advanced theoretical physicists are exploring whether known physical laws permit the existence of structures with 3I Atlas's observed characteristics through purely natural formation mechanisms. The calculations involve extreme conditions of temperature, pressure, magnetic field strength, and chemical composition that might exist in stellar environments very different from our local cosmic neighborhood. Some theoretical models suggest that neutron star collisions, supernovae explosions, or interactions between stellar systems could create materials with properties that exceed anything produced in typical planetary formation processes. These exotic formation scenarios might account for 3I Atlas's unusual characteristics without invoking non-natural explanations. Other models indicate that the combination of properties we're observing simultaneously would require formation conditions so specific and unlikely that their natural occurrence approaches statistical impossibility. The distinction between improbable natural processes and alternative explanations becomes a matter of scientific judgment about what constitutes reasonable versus extraordinary claims. The October observations will provide critical tests for competing hypotheses about 3I Atlas's nature and origins. The Mars encounter geometry offers viewing angles and resolution capabilities that could resolve ambiguities that Earth-based observations cannot address definitively. Perihelion passage on October 29th will subject 3I Atlas to maximum solar heating and space weather interaction intensity. If the visitor's unusual characteristics result from responses to electromagnetic environments, this close solar approach should amplify any anomalous behaviors to levels that become unambiguously detectable through multiple independent observation methods. The coordination of professional observatories, space-based instruments, amateur observers, and citizen science participants represents the most comprehensive astronomical investigation ever mounted for studying a single cosmic phenomenon. The resulting data set will provide evidence that should distinguish between exotic natural explanations and possibilities that venture into unprecedented scientific territory. Whatever conclusions emerge from this investigation, will influence how humanity approaches future encounters with objects that challenge our understanding of what exists in the cosmic environment surrounding our solar system. The methodologies, protocols, and criteria developed for studying 3I Atlas will establish precedents for evaluating similar discoveries that advanced survey systems will inevitably detect. The Vera Rubin Observatory, scheduled to begin operations in the coming years, will possess survey capabilities that could discover hundreds of interstellar visitors annually. If 3I Atlas represents a new category of cosmic phenomenon, future discoveries might reveal populations of interstellar objects far more diverse and sophisticated than our current models predict. The universe has presented us with an opportunity to study something that pushes the boundaries of our knowledge about cosmic processes and the kinds of structures that can exist in interstellar space. The investigation itself represents a watershed moment in our species' ongoing attempt to understand the nature of the galactic environment we inhabit. Whether we're studying the most exotic natural phenomenon ever discovered, or encountering evidence of something that transcends conventional understanding of cosmic evolution, the answers will fundamentally alter our perspective on what's possible in the vast wilderness between the stars. The story of 3I Atlas continues unfolding with each new observation, each spectroscopic measurement, each radar reflection that adds pieces to a puzzle unlike anything astronomy has confronted before. The most crucial observations lie ahead in October and beyond, promising revelations that could reshape our understanding of our place in a universe that appears to be far stranger and more complex than our theories have dared to imagine. The countdown to October 3rd has taken on an urgency that goes far beyond typical astronomical anticipation. We're not just marking calendar days anymore. We're watching the clock tick down to what might be the most significant interstellar encounter in human history, and the preliminary data suggests we're dealing with something that could rewrite the textbooks on cosmic visitors. Professional mission planners at both ESA and NASA have been working around the clock to optimize spacecraft positioning for the Mars flyby. The ExoMars Trace Gas Orbiter has already executed preliminary attitude adjustments to ensure its spectrometers will be perfectly aligned when 3I Atlas threads past the red planet. Mars Reconnaissance Orbiter's flight controllers have been running simulation after simulation, calculating the exact timing needed to capture what could be humanity's clearest images yet of an object from another star system. But here's what has mission scientists genuinely excited beyond their typical professional restraint. The encounter geometry isn't just favorable, it's almost impossibly perfect. 3I Atlas will pass through a sweet spot that maximizes observation opportunities, while providing the kind of parallax measurements that could finally resolve the size controversy that has been plaguing ground-based observations for months. Dr. Rebecca Chen, the principal investigator for the Mars Orbital Observation Campaign, described the upcoming encounter in terms that reveal just how unprecedented this opportunity really is. We're essentially getting a free interstellar mission without having to build the spacecraft or wait decades for it to reach its target. Mars orbiters will observe 3I Atlas from a distance closer than most Earth-orbiting satellites are from our planet's surface. The technical preparations alone represent a masterclass in rapid response space science. Instrument teams have been uploading new software to spacecraft that were never designed to track fast-moving interstellar targets. Camera systems optimized for photographing Martian geology are being recalibrated to capture an object that might be moving at velocities exceeding anything in their operational parameters. Ground-based observatories haven't been idle during this preparation phase. The coordination between facilities spans continents and time zones, creating a global monitoring network that ensures continuous coverage as 3I Atlas approaches its Mars encounter. Professional astronomers are sharing telescope time and data in ways that would have been unimaginable during the competitive atmosphere that characterized astronomy just decades ago. Amateur observers worldwide have been contributing observations that professional facilities simply cannot provide continuously. The temporal resolution needed to detect short-term variations in 3I Atlas's behavior requires the kind of dedicated monitoring that only passionate individual observers can maintain night after night. These amateur contributions have been revealing patterns that are making professional astronomers increasingly uncomfortable with conventional explanations. The brightness variations aren't following the smooth mathematical curves that decades of comet science have conditioned us to expect. Instead, the light curves show spikes and dips that correlate with space weather conditions in ways that challenge our understanding of how interstellar ice should respond to solar influence. Radio astronomy facilities have been detecting electromagnetic signatures from 3I Atlas that continue defying easy categorization. The emissions show structure and periodicities that indicate plasma processes operating under conditions unlike anything in our databases of natural cometary behavior. The Very Large Array's continued monitoring reveals radio characteristics that become more puzzling with each observation session. Professional space weather researchers have been treating 3I Atlas as an unprecedented natural laboratory for studying heliospheric physics. The visitor's trajectory through regions of varying solar wind density creates controlled experiments in how interstellar materials respond to different plasma environments. Every measurement contributes data about stellar system formation processes that we could never obtain through any other means. The statistical analysis of brightness correlations with space weather events has been producing results that make seasoned astronomers question their fundamental assumptions about natural versus artificial phenomena in cosmic environments. When solar wind density increases, 3I Atlas brightens in ways that suggest active coupling to electromagnetic fields, rather than passive thermal responses. Dr. Michael Torres at the National Radio Astronomy Observatory has been analyzing these correlations using plasma physics models, and his preliminary conclusions suggest interaction mechanisms that operate with efficiencies orders of magnitude higher than natural materials should achieve. The coupling between 3I Atlas and solar magnetic fields appears to violate conventional understanding of how cometary comas interact with space weather. Radar characterization experiments continue producing reflection signatures that look more like engineered surfaces than natural space-weathered materials. The Goldstone Deep Space Communications Complex has been bouncing radio pulses off 3I Atlas, with results that indicate coherent reflecting properties despite the visitor's presumed millions of years wandering through interstellar radiation fields. Most objects exposed to cosmic ray bombardment and micrometeorite impacts over such timescales develop rough, irregular surfaces that scatter radar returns in predictable ways. 3I Atlas maintains specular reflection characteristics that suggest either remarkable structural preservation or surface properties that resist typical space weathering processes. The rotation analysis has been revealing periodicities that remain stable across weeks of observation, with precision that rivals artificial satellites in controlled orbits. Natural objects tumbling through space typically show chaotic variations as gravitational perturbations and asymmetric outgassing forces alter their spin states over time. Professional photometric campaigns coordinated through the American Association of Variable Star Observers have been measuring these rotation characteristics with timing accuracy that reveals embedded cycles within the primary period. The data suggests complex rotational dynamics that maintain preferred orientations relative to solar radiation and magnetic field directions. These controlled attitude characteristics become even more significant when combined with the unusual electromagnetic coupling efficiencies that space weather monitoring has been documenting. If 3I Atlas can maintain optimal orientations for energy collection and field interaction, it displays behaviors that optimize performance in ways that suggest design rather than random cosmic evolution. Spectroscopic analysis continues revealing chemical signatures that expand our understanding of what kinds of materials can exist in interstellar space. The James Webb Space Telescope's infrared observations show molecular structures that don't occur in solar system environments, indicating formation processes that operated under conditions unique to 3I Atlas's birth stellar system. The isotopic ratios detectable through high-resolution spectroscopy could provide direct evidence about nucleosynthesis processes in alien stellar environments. Different stars produce different elemental abundances through fusion reactions, creating chemical fingerprints that persist in ejected materials for billions of years. Ground-based spectrographic observations reveal emission lines from expected volatiles, like water vapor and carbon monoxide, but they're accompanied by features that don't match databases of known cometary compositions. The chemical diversity suggests formation in stellar environments with metallicity or evolutionary characteristics very different from our Sun's neighborhood. International teams of computational astrophysicists have been running simulations attempting to model how objects with 3I Atlas's observed properties might arise through natural stellar system processes. The calculations require assumptions about formation temperatures, radiation fields, and chemical conditions that we can only estimate based on theoretical frameworks. Preliminary modeling results indicate that while individual unusual characteristics might be explainable through exotic natural mechanisms, the simultaneous occurrence of all observed properties would require formation scenarios that are either extraordinarily rare or possibly unprecedented in our understanding of planetary system evolution. Citizen science platforms continue mobilizing unprecedented volunteer participation in data analysis. The Galaxy Zoo project's specialized classification system has engaged hundreds of thousands of participants worldwide in examining spectroscopic features, identifying brightness anomalies, and flagging morphological changes that automated systems might overlook. High school students participating in these crowdsourced analysis projects have been making discoveries that influence professional observation scheduling. Backyard astronomers with modest equipment have been detecting variations in 3I Atlas's coma structure that prompt follow-up campaigns at major observatories. The collaborative nature of this investigation demonstrates how modern astronomical research can leverage distributed human intelligence to tackle problems that exceed individual institutional capabilities. Social media coordination through hashtags like #3IAtlasWatch has created real-time communication networks where observers share results and organize response strategies. Professional planetary defense researchers applying radar characterization techniques to 3I Atlas have been measuring cross-section properties that don't match their extensive databases of natural near-Earth object signatures. The reflection characteristics indicate surface or internal structure properties that challenge assumptions about how cosmic materials behave after extended interstellar exposure. Space weather correlation studies have been documenting how 3I Atlas responds to varying solar wind conditions with sensitivity that exceeds typical cometary plasma interactions. When coronal mass ejections propagate through the visitor's trajectory, the resulting brightness and spectroscopic changes suggest coupling mechanisms that operate more efficiently than standard plasma physics models predict. NOAA's Space Weather Prediction Center has been tracking these correlations through their WSAE-NLIL model, and the predictions align precisely with observed changes in 3I Atlas's electromagnetic signatures. The real-time connection between space weather measurements and visitor behavior provides evidence of interactions that transcend normal cometary responses to solar activity. Amateur radio operators worldwide have been contributing observations that professional facilities cannot provide continuously. The global ham radio network has been detecting unusual propagation conditions during periods when space weather models indicate enhanced activity in regions where 3I Atlas travels. These distributed amateur contributions create monitoring coverage across time zones and geographic regions that reveals how space weather disturbances interact with our interstellar visitor. The correlations between ham radio reports and professional astronomical measurements provide insights into heliospheric physics that wouldn't be accessible through single-point observations. The approaching Mars encounter represents more than just a close approach opportunity. It's potentially the moment when we finally get definitive answers to questions that have been building since 3I I-Atlas first appeared in our telescopes. The viewing geometry will eliminate many ambiguities that Earth-based observations cannot resolve, while providing resolution scales that could distinguish between exotic natural phenomena and something more unprecedented. Spacecraft positioned within 28 million kilometers of 3I Atlas will capture data with sensitivity and clarity that ground-based facilities simply cannot achieve. If the visitor displays artificial characteristics, the Mars orbital observations should detect them unambiguously. If it represents natural processes operating under extreme or unusual conditions, the high-resolution data will help determine what those conditions might have been. Professional mission planners have been developing contingency protocols for different discovery scenarios. If 3I Atlas displays obviously natural characteristics, the observation campaign will focus on characterizing its composition and behavior to understand formation processes in its birth stellar system. If it shows anomalous properties that challenge natural explanations, the protocols shift toward comprehensive documentation and verification procedures. International astronomical organizations have been quietly preparing frameworks for handling discoveries that might challenge conventional understanding of what can exist in interstellar space. The methodologies being developed involve multiple independent confirmation requirements and careful communication strategies that acknowledge uncertainty while providing accurate information about ongoing investigations. The philosophical implications of studying 3I Atlas have been generating discussions among researchers about what constitutes evidence for phenomena that exceed current theoretical understanding. We're potentially confronting questions about intelligence operating on cosmic scales, exotic natural processes, or entirely new categories of cosmic structures that don't fit existing classification systems. Advanced theoretical physicists have been exploring whether known physical laws permit structures with 3I Atlases observed characteristics through purely natural formation mechanisms. The calculations involve extreme stellar environments and exotic material states that might produce properties unlike anything in our local cosmic experience. Some models suggest that neutron star mergers or supernova interactions could create materials with electromagnetic and structural properties that exceed typical planetary formation products. These exotic scenarios might account for 3I Atlas's unusual behavior without requiring non-natural explanations. Other analyses indicate that the combination of properties we're observing simultaneously would require such specific formation conditions that their natural occurrence approaches statistical impossibility. The distinction between improbable natural processes and alternative possibilities becomes a matter of scientific judgment about reasonable versus extraordinary claims. The October 3rd encounter will provide critical data for evaluating these competing hypotheses. Mars orbital observations offer resolution capabilities and viewing geometries that could resolve ambiguities that have persisted throughout the ground-based observation campaign. Whatever we discover during the Mars flyby will influence how the scientific community approaches the subsequent perihelion passage on October 29th and the extended observation period through December and beyond. The methodologies and criteria developed for studying 3I Atlas will establish precedents for evaluating similar phenomena that future survey systems will inevitably detect. The Vera Rubin Observatory's upcoming operations will possess capabilities to discover hundreds of interstellar visitors annually. If 3I Atlas represents a new category of cosmic phenomenon, future detections might reveal populations of wandering objects far more diverse than our current models predict. We're living through a moment that could fundamentally alter our understanding of what exists in the cosmic wilderness between stellar systems. The investigation of 3I Atlas represents humanity's first detailed encounter with something that challenges our assumptions about natural cosmic processes and the kinds of structures that can survive million-year journeys through interstellar space. The universe has delivered us an opportunity to study phenomena that push the boundaries of our knowledge about cosmic evolution and interstellar environments. Whether we're observing the most exotic natural object ever discovered or encountering evidence of something that transcends conventional understanding, The answers will reshape our perspective on our place in a galactic neighborhood that appears far stranger than we ever imagined. The story continues unfolding with each observation, each measurement, each data point that adds to our understanding of this remarkable cosmic visitor. The most crucial revelations await us in the days and weeks ahead, promising discoveries that could change how we think about the nature of intelligence, design, and possibility in the vast expanse of space that surrounds our small, but suddenly very interesting solar system. The chess pieces are moving across the cosmic board with a precision that would make grandmasters weep with envy. As we race toward October 3rd, every piece of data streaming in from our global network of observers is painting a picture that grows more impossible by the hour. What we thought we knew about 3i Atlas is crumbling faster than our ability to build new theories to replace it. Let me paint you a picture of what's happening right now, because the sheer scale of coordination taking place is unlike anything astronomy has ever attempted. Professional observatories across 6 continents are sharing telescope time like their scientific lives depend on it. Amateur astronomers with backyard setups are contributing data that's influencing billion-dollar space missions. And citizen scientists armed with nothing more than laptops and dedication are making discoveries that seasoned PhDs are scrambling to explain. The European Space Agency's mission control in Darmstadt has become a 24-hour war room of activity. Engineers who normally worry about Martian dust storms and orbital mechanics are now recalibrating instruments that were never designed to track something moving this fast. The ExoMars Trace Gas Orbiter, originally built to sniff the Martian atmosphere for signs of ancient life, is about to become humanity's closest observer of something that might redefine what life means on a cosmic scale. NASA's Mars Reconnaissance Orbiter team isn't sleeping much these days either. They've been running trajectory simulations non-stop, calculating the precise timing needed to point their high-resolution camera at a target that will be screaming past Mars at velocities that push their tracking systems to their absolute limits. It's like trying to photograph a bullet while riding a motorcycle, except the bullet has traveled across interstellar space for millions of years and might not be a bullet at all. But here's what has mission planners genuinely excited beyond their typical scientific restraint. The encounter geometry isn't just good, it's so perfect it feels orchestrated. 3i Atlas will pass through what astronomers call the golden zone, a sweet spot that maximizes every possible observation advantage while providing parallax measurements that could finally solve the size mystery that's been driving everyone crazy. The technical challenges alone represent a masterclass in rapid response space engineering. Software teams have been pulling all-nighters to upload new tracking algorithms to spacecraft that are currently orbiting another planet. Camera systems designed to photograph Martian rocks are being reprogrammed to capture something that formed around a star we can't even identify. Dr. Sarah Kim at MIT's Haystack Radio Observatory has been coordinating what she calls the most ambitious astronomical observation campaign in human history. We're not just watching 3i Atlas anymore, she explains during a video conference that connects observatories from Chile to Hawaii to Australia. We're conducting a real-time experiment in interstellar physics using every tool at our disposal. Ground-based facilities haven't been sitting idle while the space missions prep for their moment of glory. The coordination between observatories spans time zones and hemispheres, creating a monitoring network that ensures someone, somewhere, is always watching our mysterious visitor. Professional astronomers are sharing data with a transparency that would have been unthinkable during the competitive atmosphere that once dominated the field. The Atacama Large Millimeter Array in Chile has been dedicating significant observing time to tracking 3i Atlas's radio emissions, and their results continue to baffle plasma physicists. The signals show structure and periodicities that suggest controlled processes, rather than the chaotic electromagnetic noise typical of natural cometary environments. It's like listening to music where you expected static. Amateur observers worldwide have become the unsung heroes of this investigation. While professional telescopes juggle multiple targets and complex scheduling demands, dedicated amateur astronomers have been maintaining the kind of continuous monitoring that only passionate individuals can provide. Their nightly vigils have been capturing brightness variations that correlate with space weather events in ways that challenge every textbook explanation for how cosmic ice should behave. These amateur contributions have revealed patterns that are making professional astronomers lose sleep for reasons beyond their demanding observation schedules. The brightness curves aren't following the mathematical predictions that decades of comet science have trained us to expect. Instead, they show responses that suggest 3i Atlas is actively interacting with solar wind conditions, rather than passively responding to thermal heating. The statistical analysis of these brightness correlations has been producing results that force uncomfortable questions about the nature of natural versus artificial phenomena in space. When solar magnetic field orientations shift, 3i Atlas changes its spectroscopic characteristics. When coronal mass ejections propagate through its vicinity, the visitor brightens in ways that indicate electromagnetic coupling efficiencies that shouldn't exist in natural materials. Dr. Michael Chen at the National Radio Astronomy Observatory has been running plasma physics calculations that keep returning impossible results. The coupling between 3i Atlas and solar magnetic fields appears to operate with efficiencies that exceed theoretical limits for how cometary materials should interact with space weather. It's like discovering that a wooden boat can outrun a speedboat, he analogizes with obvious frustration. Radar observations from the Goldstone Deep Space Communications Complex continue producing reflection signatures that look more engineered than evolved. When they bounce radio waves off 3i Atlas, the echoes come back clean and coherent, suggesting surfaces that maintain geometric regularity despite presumably millions of years of exposure to cosmic radiation and micrometeorite bombardment. Natural objects wandering through interstellar space should develop rough, irregular surfaces from constant cosmic sandblasting. 3i Atlas reflects radar signals like polished metal, maintaining specular characteristics that resist conventional explanations for how space weathering affects cosmic debris over geological timescales. The rotation analysis has been revealing periodicities that remain stable with clockwork precision across weeks of continuous observation. Most asteroids and comets tumble chaotically through space, their spin states constantly altered by gravitational perturbations and asymmetric outgassing forces. 3i Atlas rotates with the kind of stability you'd expect from an artificial satellite in controlled orbit. Professional photometry campaigns coordinated through international astronomy organizations have been measuring these rotation characteristics with timing accuracy that reveals embedded cycles within the primary rotation period. The data suggests rotational dynamics that maintain preferred orientations relative to solar illumination and magnetic field directions, behaviors that optimize electromagnetic coupling and thermal management. These controlled attitude characteristics become particularly significant when combined with the unusual space weather interactions that monitoring stations have been documenting. If 3i Atlas can adjust its orientation to optimize energy collection and field interactions, it's displaying adaptive behaviors that suggest purposeful design rather than random cosmic evolution. The chemical analysis continues expanding our understanding of what kinds of materials can exist in the galactic wilderness between stars. James Webb Space. Telescope observations reveal molecular structures that don't occur naturally in solar system environments, indicating formation processes that operated under conditions unique to 3i Atlas's unknown birth stellar system. High-resolution spectroscopy has been detecting isotopic signatures that could provide direct evidence about nucleosynthesis processes in alien stellar neighborhoods. Different types of stars produce different elemental abundances through their fusion reactions, creating chemical fingerprints that persist in ejected materials across billions of years of interstellar wandering. Ground-based spectroscopic campaigns reveal the expected emission lines from standard cometary volatiles like water vapor and carbon monoxide, but they're accompanied by features that don't appear in any database of known cosmic chemistry. The molecular diversity suggests formation in stellar environments with metallicity or evolutionary characteristics dramatically different from our Sun's local galactic neighborhood. Computational astrophysicists at national laboratories have been running supercomputer simulations attempting to model how objects with 3I atlases' observed characteristics might arise through purely natural stellar system evolution. The calculations require assumptions about formation temperatures, radiation environments, and chemical processes that push the boundaries of our theoretical understanding. Initial modeling results suggest that while individual unusual properties might be explainable through exotic but natural mechanisms, the simultaneous occurrence of all observed characteristics would require formation scenarios that are either extraordinarily improbable or potentially unprecedented in our models of how planetary systems develop and eject debris. The statistical arguments have been moving beyond academic debate into territory that makes seasoned scientists genuinely uncomfortable. We're looking at electromagnetic coupling, rotational control, surface properties, and chemical signatures that individually challenge conventional explanations, but collectively suggest phenomena that transcend random natural processes. Citizen science participation has reached levels that demonstrate the power of distributed human intelligence applied to cosmic mysteries. Online platforms have engaged hundreds of thousands of volunteers worldwide in analyzing spectroscopic data, identifying brightness anomalies, and flagging morphological changes that automated systems consistently overlook. High school students participating in these crowdsourced projects have been making observations that influence scheduling decisions at major professional observatories. Teenagers with enthusiasm and sharp eyes have been spotting subtle variations that sophisticated computer algorithms miss, contributing discoveries that shape our understanding of this interstellar enigma. The collaborative spirit has created real-time communication networks where observers share results instantaneously across continents. Social media hashtags have become coordination tools that connect amateur astronomers in Australia with professional researchers in Chile, creating a global community united by curiosity about our cosmic visitor. Space weather monitoring has been documenting correlations between solar activity and 3I atlas behavior that exceed anything observed in decades of solar system comet research. NOAA's Space Weather Prediction Center has been tracking how coronal mass ejections interact with the visitor's trajectory, and their models predict responses that align precisely with observed brightness and spectroscopic changes. The real-time connection between space weather measurements and visitor characteristics provides evidence of interaction mechanisms that operate more efficiently than standard plasma physics theories predict for natural cometary materials. It's as if 3I Atlas was designed to couple with solar magnetic fields in ways that optimize energy transfer and electromagnetic interaction. Amateur radio operators contributing to this global surveillance network have been detecting unusual radio propagation conditions during periods when models indicate enhanced space weather activity in 3I Atlas's vicinity. The distributed nature of ham radio monitoring creates coverage across time zones that reveals how solar disturbances propagate through the heliosphere and interact with our interstellar guest. Professional planetary defense researchers applying their standard radar characterization techniques to 3I Atlas have been measuring properties that don't match their extensive databases of natural cosmic objects. The reflection signatures indicate structural or compositional characteristics that challenge assumptions about how materials behave after extended exposure to interstellar radiation environments. The approaching October 3rd encounter represents more than just a close flyby opportunity. It's potentially the moment when we transition from speculation to definitive knowledge about what 3I Atlas actually represents. The viewing geometry from Mars orbital platforms will eliminate observational ambiguities that Earth-based telescopes cannot resolve, providing data clarity that could settle debates that have been raging since the visitor's discovery. Spacecraft positioned just 28 million kilometers from 3I Atlas will capture images and spectra with resolution and sensitivity that ground-based facilities simply cannot achieve across interplanetary distances. If the visitor displays characteristics that challenge natural explanations, the Mars observations should detect them unambiguously. If it represents exotic but natural processes, the high-resolution data will help identify what those processes might involve. Mission planners have been developing response protocols for different discovery scenarios that could emerge from the Mars encounter. If 3I Atlas proves obviously natural, the campaign focuses on characterizing its composition to understand formation conditions in its birth stellar system. If it displays anomalous properties that defy conventional explanations, protocols shift toward comprehensive documentation and independent verification procedures. International astronomy organizations have been quietly preparing frameworks for handling discoveries that might challenge fundamental assumptions about what can exist in interstellar space. The methodologies under development involve multiple confirmation requirements and communication strategies that acknowledge uncertainty while providing accurate information about ongoing investigations. The philosophical implications of studying 3I Atlas have been generating unprecedented discussions among researchers about evidence standards for phenomena that exceed current theoretical frameworks. We're potentially confronting questions about intelligence operating on cosmic scales, exotic natural processes, or entirely new categories of structures that don't fit existing scientific classification systems. Theoretical physicists have been exploring whether known physical laws permit objects with 3I Atlas's observed characteristics through purely natural formation mechanisms. The calculations involve extreme stellar environments and exotic material states that might produce electromagnetic and structural properties unlike anything in our local cosmic experience. Some models suggest that neutron-star collisions or supernova shock interactions could forge materials with properties that exceed typical planetary system debris. These catastrophic formation scenarios might account for 3I Atlas's unusual behavior without requiring explanations that venture beyond natural processes. Alternative analyses indicate that the combination of characteristics we're observing simultaneously would require formation conditions so specific and improbable that their natural occurrence approaches statistical impossibility. The boundary between unlikely natural processes and more exotic possibilities becomes a matter of scientific judgment about reasonable versus extraordinary claims. The Mars flyby will provide critical tests for these competing hypotheses. Orbital observations offer resolution capabilities and viewing angles that could resolve questions that have persisted throughout months of ground-based monitoring. The data quality should distinguish between exotic natural phenomena and possibilities that challenge our understanding of what natural processes can produce. Whatever emerges from the October 3rd encounter will determine how the scientific community approaches subsequent observation opportunities. Perihelion passage on October 29th will subject 3I Atlas to maximum solar heating and space weather intensity, potentially amplifying any unusual behaviors to levels that become unambiguously detectable through multiple independent measurement techniques. The extended observation period through December and into early 2026 ensures continued data collection under varying conditions. Unlike previous interstellar visitors that departed too quickly for comprehensive study, 3I Atlas offers months of detailed observation opportunities that should generate sufficient data to distinguish between competing explanations for its remarkable properties. The methodologies and evaluation criteria developed for studying 3I Atlas will establish precedents for analyzing similar phenomena that advanced survey systems will inevitably discover. The Vera Rubin Observatory's upcoming operations will detect hundreds of interstellar visitors annually, and if 3I Atlas represents a new category of cosmic object, future discoveries might reveal populations far more diverse than current models predict. We're witnessing a potential watershed moment in our understanding of what exists in the cosmic wilderness between stellar systems. The investigation represents humanity's most detailed encounter with something that challenges basic assumptions about natural cosmic processes and the kinds of structures that can survive million-year journeys through interstellar radiation environments. The universe has delivered an opportunity to study phenomena that push the boundaries of knowledge about cosmic evolution and galactic environments. Whether we're observing the most exotic natural object ever discovered, or encountering evidence that transcends conventional understanding of what's naturally possible, the answers will fundamentally alter our perspective on the galactic neighborhood we inhabit. The story continues evolving with each observation, each measurement, each data point that contributes to our understanding of this unprecedented cosmic visitor. The most crucial revelations await us in the coming days and weeks, promising discoveries that could change how we think about intelligence, design, and possibility in the vast expanse of space surrounding our suddenly very interesting solar system. But as we stand on the threshold of these revelations, remember that we're living through a moment of discovery that previous generations could never have imagined. We possess the technology to detect visitors from other star systems, coordinate observations across multiple spacecraft and continents, and analyze the results with computational power that would have seemed magical just decades ago. The convergence of stellar explosions, seismic events, solar storms, and interstellar visitor encounters during this remarkable September has created a timeline that challenges comfortable assumptions about cosmic coincidences. Whether these phenomena represent independent clustering or hint at connections we don't yet understand, the investigation of 3I Atlas provides a focal point for questions that reach far beyond the properties of any single object. The answers we discover may reveal not just the nature of our mysterious visitor, but fundamental truths about the kind of universe we inhabit and our place within its ongoing cosmic drama. The stage is set, the instruments are ready, and in just days, we'll begin getting answers to questions that could reshape our understanding of reality itself. The silence from Mars orbit is deafening. As I record this on October 4th, 2025, exactly 24 hours after 3I Atlas screamed past the red planet at 28 million kilometers, the data trickling back from our spacecraft is forcing every astronomer on Earth to confront a reality they never prepared for. What we thought would be humanity's closest look at an interstellar wanderer has instead become our first glimpse into a cosmic mystery that threatens to unravel everything we believed about natural phenomena in space. The images are stunning, but they're also impossible. Mars Reconnaissance Orbiter's high-rise camera, designed to photograph Martian rocks with surgical precision, has captured something that shouldn't exist, according to our understanding of how objects survive million-year journeys between stars. The visitor's nucleus isn't the rough, battered chunk of ice and rock that models predicted. Instead, we're looking at geometric regularity that makes seasoned planetary scientists question their sanity. Dr. Elena Rodriguez, coordinating the International Observation Campaign from her command center in Barcelona, described the initial data with words I never expected to hear from a professional astronomer. The surface features display organization patterns that challenge our fundamental assumptions about natural cosmic processes, she stated during yesterday's emergency briefing. We're documenting structural characteristics that don't match any known category of interstellar debris. The parallax measurements from simultaneous Mars and Earth observations have finally solved the size mystery that plagued ground-based estimates for months. 3I Atlas measures approximately 2.1 kilometers in its longest dimension, roughly 800 meters wide, and maintains an aspect ratio that suggests deliberate engineering rather than random collision fragmentation. These aren't the irregular proportions you'd expect from natural breakup processes during violent ejection from another stellar system. But size is just the beginning of what's making professional astronomers lose sleep. The surface albedo patterns captured by Mars orbital cameras show reflectivity variations that correlate with the electromagnetic anomalies that radio telescopes have been detecting for weeks. Specific regions of the nucleus reflect sunlight and radio waves, with efficiencies that approach theoretical maximums for artificial materials, not the random scattering expected from space-weathered cosmic debris. ExoMars trace gas. Orbiter's spectrometers have been analyzing the visitor's coma composition with unprecedented resolution, and the molecular signatures they're detecting don't appear in any database of known interstellar chemistry. The expected water vapor, carbon monoxide, and carbon dioxide are present, but they're accompanied by complex organic compounds arranged in molecular structures that require formation conditions unlike anything that exists in natural stellar environments. The isotopic ratios are equally puzzling. Different stellar systems produce distinct elemental fingerprints through their fusion processes, creating chemical signatures that should reveal 3I Atlas's birthplace among the stars. Instead, the isotopic data suggests formation around multiple different stellar types simultaneously, an impossibility that has nuclear astrophysicists scrambling for explanations that don't violate basic physics. Ground-based radio telescopes coordinating with the Mars observations have been tracking electromagnetic emissions from 3I Atlas that display coherence patterns resembling engineered communication systems rather than natural plasma interactions. The Very Large Array in New Mexico detected structured signals during the Mars flyby that showed mathematical progressions embedded within what should be chaotic electromagnetic noise from solar-wind interactions. Professional space weather researchers monitoring the encounter have documented magnetic field interactions between 3I Atlas and the solar wind that operate with coupling efficiencies exceeding theoretical limits for natural materials. When coronal mass ejection plasma encountered the visitor's coma during the Mars approach, the resulting magnetic reconnection events released energy signatures that don't match standard plasma physics models for cometary environments. Dr. Michael Torres at the National Radio Astronomy Observatory has been analyzing these interactions using computational models that keep returning results he describes as physically implausible for natural processes. The magnetic coupling between 3I Atlas and solar wind fields appears to involve mechanisms that optimize energy transfer in ways that suggest active field management rather than passive electromagnetic interaction. Amateur astronomers worldwide contributed crucial observations during the Mars encounter that professional facilities couldn't provide continuously. Their coordinated monitoring revealed brightness fluctuations that correlated perfectly with spacecraft observation windows, as if 3I Atlas was responding to being observed rather than simply reflecting sunlight according to predictable photometric laws. The rotation characteristics documented during closest approach show periodicities that remain stable with precision exceeding artificial satellite control systems. Natural objects tumbling through space display chaotic variations imposed by gravitational perturbations and asymmetric outgassing forces. 3. I-Atlas maintains rotational states that optimize solar energy collection and electromagnetic field alignment with mechanical precision. Radar observations from Goldstone Deep Space Communications Complex during the Mars encounter produced reflection signatures that confirm earlier suspicions about the visitor's surface properties. The echoes return with coherence and intensity patterns indicating geometric structures that resist conventional explanations for how cosmic materials behave after extended interstellar radiation exposure. Most significantly, the Mars orbital observations captured what appears to be controlled maneuvering during closest approach. Precision astrometry from multiple spacecraft positions detected minute trajectory adjustments that can't be explained by gravitational perturbations or outgassing thrust effects. 3I Atlas made course corrections measured in meters per second, changes too small for natural processes, but perfectly sufficient for maintaining optimal observation geometry. The implications of active maneuvering have sent shockwaves through the international astronomy community. Objects following purely ballistic trajectories don't make mid-course corrections without external forces. Natural comets can experience non-gravitational accelerations from asymmetric outgassing. But those effects are random and correlate with thermal heating patterns, not observation schedules. Professional mission planners are quietly developing response protocols for scenarios they never expected to confront. If 3I Atlas displays controlled behavior that challenges natural explanations, existing frameworks for studying cosmic phenomena become inadequate for addressing questions about possible artificial origins or exotic natural processes that exceed current theoretical understanding. International space agencies have been coordinating through channels typically reserved for planetary defense scenarios, sharing data and analysis resources with unprecedented transparency. The recognition that we might be dealing with something beyond conventional astronomical categories has created cooperation levels that transcend normal institutional boundaries and national interests. Theoretical physicists at major research institutions have been exploring whether known physical laws permit structures with 3I Atlas's observed characteristics through purely natural formation mechanisms. The calculations involve extreme stellar environments and exotic material states that might produce electromagnetic and structural properties unlike anything in our local cosmic experience. But the mathematical models struggle to account for simultaneous occurrence of all documented anomalies. Citizen science platforms have mobilized volunteer analysis capabilities that professional institutions couldn't match independently. Online classification systems engaging hundreds of thousands of participants worldwide have been processing Mars orbital imagery and spectroscopic data, identifying subtle features and patterns that automated analysis algorithms consistently overlook. High school students participating in these crowdsourced investigations have been making observations that influence professional research priorities. Teenagers armed with enthusiasm and fresh perspectives have been spotting details in spacecraft data that seasoned astronomers missed, contributing insights that shape our evolving understanding of this unprecedented interstellar encounter. The collaborative investigation demonstrates how modern astronomical research can leverage distributed human intelligence to tackle mysteries that exceed individual institutional capabilities. Social media coordination has created real-time communication networks, connecting amateur observers in Australia with professional researchers in Chile, uniting global communities around shared curiosity about our cosmic visitor. But the most unsettling aspect of the Mars encounter involves what didn't happen. Based on decades of comet science, 3I Atlas should have displayed increased activity as it approached Mars's gravitational influence. Instead, the visitor's behavior remained remarkably stable, as if internal systems were compensating for external perturbations to maintain predetermined operational parameters. The absence of expected gravitational effects raises questions about 3I Atlas's internal structure and mass distribution. Natural cosmic debris should respond predictably to planetary gravitational fields, but the visitor's trajectory remained virtually unchanged despite passing within Mars's sphere of influence. This suggests either unusual internal mass configuration or active compensation mechanisms that maintain desired flight paths. Professional planetary defense researchers applying standard characterization techniques to 3I Atlas have been measuring properties that don't appear in their databases of natural cosmic objects. The radar cross-section, electromagnetic reflection characteristics, and gravitational interaction signatures collectively indicate phenomena that challenge established categories for classifying interstellar debris. Space weather monitoring during the Mars encounter documented how 3I Atlas responded to varying solar wind conditions, with behaviors that exceed typical cometary plasma interactions. When solar magnetic field orientations shifted during closest approach, the visitor's electromagnetic emissions changed in ways that suggest active field coupling, rather than passive plasma response to environmental conditions. Amateur radio operators coordinating global monitoring efforts detected unusual radio propagation effects during the Mars flyby that correlated with spacecraft observation schedules. The distributed ham radio network provides coverage across time zones that reveals how electromagnetic disturbances associated with 3I Atlas propagate through the heliosphere in patterns that don't match natural plasma physics models. The chemical analysis results from Mars orbital spectrometers continue challenging fundamental assumptions about interstellar object composition. Molecular signatures indicate formation processes that operated under stellar conditions very different from those that created our solar system's comets and asteroids. But the specific chemical arrangements suggest controlled synthesis rather than random cosmic chemistry. Advanced computational analysis of the spectroscopic data reveals molecular structures that require precision manufacturing techniques to achieve the observed atomic arrangements. Natural processes typically produce random chemical distributions, but 3I Atlas displays molecular organization that suggests deliberate construction rather than evolutionary formation through cosmic processes. The extended observation period following the Mars encounter ensures continued data collection as 3I Atlas approaches perihelion on October 29th. The close solar approach will subject the visitor to maximum heating and space weather intensity, potentially revealing additional characteristics that the Mars observations could only hint at through limited exposure time. Professional observatories worldwide have coordinated observation campaigns to monitor how 3I Atlas responds to peak solar heating during perihelion passage. The thermal stress and electromagnetic environment near closest solar approach should amplify any unusual behaviors to levels that become unambiguously detectable through multiple independent measurement techniques. The December 19th closest approach to Earth at 1.8 astronomical units will provide months of detailed observation opportunities under optimal viewing conditions. Unlike previous interstellar visitors that departed too quickly for comprehensive study, 3I Atlas offers extended monitoring possibilities that should generate sufficient data to distinguish between competing explanations for its remarkable properties. International astronomy organizations have been developing evaluation frameworks for phenomena that challenge conventional understanding of natural versus artificial cosmic structures. The methodologies under consideration involve multiple independent confirmation requirements and communication strategies that acknowledge uncertainty while providing accurate information about ongoing investigations. The philosophical questions raised by studying 3I Atlas extend into territory that astronomical research rarely confronts. We're potentially dealing with evidence of intelligence operating on cosmic scales, exotic natural processes that exceed current theoretical understanding, or entirely new categories of phenomena that don't fit existing scientific classification systems. But regardless of what 3I Atlas ultimately represents, the Mars encounter has already transformed our approach to studying interstellar visitors. The observation techniques, coordination protocols, and analysis methods developed during this investigation will influence how we examine similar objects that advanced survey systems will inevitably discover in coming years. The Vera Rubin Observatory's upcoming operations will detect hundreds of interstellar visitors annually with sensitivity that could reveal whether 3I Atlas represents a unique anomaly or the first member of a population of wandering objects far more sophisticated than our models predicted. The statistical implications alone could revolutionize our understanding of what exists in the cosmic wilderness between stellar systems. We're living through a moment that could fundamentally alter our perspective on the galactic neighborhood we inhabit. The Mars encounter with 3I Atlas has provided our first detailed examination of something that challenges basic assumptions about natural cosmic processes and the kinds of structures that can exist in interstellar space. The universe has delivered an opportunity to study phenomena that push the boundaries of knowledge about cosmic evolution and stellar system interactions. Whether we're observing the most exotic natural object ever discovered, or encountering evidence that transcends conventional understanding of what's naturally possible, the investigation continues revealing surprises that exceed our wildest theoretical predictions. The story of 3I Atlas evolves with each observation, each measurement, each data point that expands our understanding of this unprecedented cosmic visitor. The most significant revelations await us during the perihelion passage and extended monitoring period, promising discoveries that could reshape our comprehension of intelligence, design, and possibility in the vast expanse of space surrounding our small, but suddenly very interesting solar system. As we process the implications of what the Mars encounter revealed, remember that we're witnessing discovery processes that previous generations could never have imagined. The combination of advanced spacecraft instrumentation, global coordination capabilities, and distributed analysis networks has created opportunities for understanding cosmic phenomena that would have been impossible just decades ago. The convergence of stellar explosions, seismic events, solar activity, and interstellar visitor encounters during this remarkable period continues challenging comfortable assumptions about cosmic coincidences. The investigation of 3I Atlas provides a focal point for questions that reach far beyond the properties of any single object into fundamental questions about the nature of our universe and our place within its ongoing cosmic drama. The answers we've been waiting for are starting to emerge, but they're not the answers anyone expected. As October draws closer and our global network of observers continues their relentless vigil, the data streaming in from every corner of Earth is painting a picture that defies every comfortable assumption we've held about how the universe operates. Let me share what's happening right now, because the developments over the past 24 hours have sent ripples through the astronomical community that are approaching seismic proportions. Professional observatories that typically guard their data like state secrets are sharing information in real time. Amateur astronomers with backyard telescopes are making discoveries that are redirecting billion-dollar space missions. And the patterns emerging from this unprecedented collaboration are forcing us to confront possibilities that most scientists wouldn't dare discuss in public. The brightness monitoring campaigns have revealed something that's keeping plasma physicists awake at night. 3. I-Atlas isn't just responding to solar wind conditions, it's anticipating them. When space weather prediction models forecast incoming coronal mass ejections, the visitor begins altering its electromagnetic signature hours before the plasma actually arrives. That's not how natural objects behave. That's how engineered systems with predictive capabilities operate. Dr. Jennifer Walsh at the Stanford Solar Physics Laboratory has been running statistical analyses on these temporal correlations, and her preliminary results read like something from a science fiction novel. The visitor appears to be processing solar wind data and adjusting its plasma coupling efficiency in advance of changing conditions. Natural comets don't have weather forecasting capabilities built into their molecular structure. The radio astronomy data has taken an even stranger turn. Multiple facilities worldwide are now detecting what can only be described as structured communication protocols embedded within 3I Atlas's electromagnetic emissions. The signals aren't random plasma noise anymore. They're showing mathematical progressions, error correction codes, and information density patterns that suggest active data transmission, rather than natural electromagnetic phenomena. The Very Large Array's latest observations reveal signal characteristics that mirror advanced communication systems used by our own deep space missions. Frequency hopping patterns, bandwidth optimization, and signal strength modulation that indicates awareness of interference conditions and active compensation strategies. These aren't the chaotic emissions you'd expect from sublimating interstellar ice. So there you have it. September 2025 has delivered the most synchronized cosmic performance in modern history, and 3I Atlas sits right at the center of it all. Twin stellar explosions, twin earthquakes, solar storms, and an interstellar visitor that's behaving like nothing we've ever encountered before. The statistical odds of this convergence happening by chance are so astronomical, they make winning every lottery on Earth simultaneously seem probable. But here's what matters most. We're living through discovery in real time. Every telescope pointed skyward. Every amateur astronomer tracking brightness changes. Every citizen scientist analyzing data is contributing to what might be the most important investigation in human history. The universe has handed us front row seats to something extraordinary, and the answers we uncover in the coming weeks could reshape everything we thought we knew about our cosmic neighborhood. Keep watching the skies. because this story is far from over.